Morning. Good morning again. Welcome to the talk about the state of hardware video codecs in Linux. My name is Andrzej Pietrasiewicz and I prepared this talk together with Nicolas Dufresne. Nicolas is a principal software engineer at Collabra, one of the top GStreamer contributors, and a kernel codec UAPI and driver contributor. I'm a senior software engineer at Collabra. I write codec drivers, and I am a co-author of the stateless VP9 decoding UAPI. We both work for Collabra, but in 2011 I was not working for Collabra. At that time, my colleagues at Samsung R&D Institute Poland were creating something that would later become the very first upstream Linux kernel driver for a hardware video codec. Were the 2011 submission and its prerequisite submissions flawless? They were not. But on the other hand, there was no prior art. Hardware video codec drivers had not existed before. Mistakes have been corrected and conclusions have been drawn. The driver is still there today, but nowadays it is not the only hardware video codec driver existing upstream. If you want to know how we got where we are with upstream support for video codecs, or you want to know what's still ahead of us in this area, or you want to know how conclusions from previous mistakes will make this future work better, then this talk is for you. But before we delve into the details, let me show you the plan of the talk. First, you will understand what is a video codec and what is a hardware video codec. Then we will talk about codec categories, which there are, and you will see example uses of codecs driven by upstream drivers in real-life applications. You will learn about the history of video codec drivers in upstream Linux kernel, and then we will try predicting the future. In about 30 minutes from now, we will be finishing with a questions and answers session. So what is a codec? It can be either of two things. It can be a specification. For example, good old JPEG spec says how to encode and decode images. It is for still images, but there exists a variant called mJPEG, which is for videos. A codec can be also an implementation of such a specification, either in software or in hardware. The hardware codecs are usually an IP block, integrated peripheral, found on an SoC system on chip. Codec specs are not terribly complicated, but usually there are a lot of variants and special cases. And it all adds up to the overall complexity. And actually, the specifications have become richer over the years too. Let's look at selected codecs to see the progression. The bars in the graph represent 1 over compression ratio, so to say, how many times is the raw data compressed. The numbers are just rough estimates to give you the general idea, rather than to precisely describe each codec performance relative to other codecs. The codecs in the graph, looking from the left, are mJPEG, which is still in use in some applications today. For example, some webcams use mJPEG. MPEG-2, by the way, the patents for MPEG-2 expired worldwide this January, except in Malaysia, where they will still be valid for the coming 11 years. So if you are not in Malaysia, you can use MPEG-2 royalty-free. Then there's H.264, also known as AVC, Advanced Video Codec, H.265, known as HEVC, High Efficiency Video Codec, AV1, and H.266, also known as VVC, Versatile Video Codec, which by some people is considered a tad better than AV1, hence 61 as the value in the graph. The efficiency of codecs, as you can see, is increasing, and so is their complexity. So it is reasonable to expect that the newer the codec, the bigger the need for it to be hardware assisted, which translates into having to provide respective drivers. But before we look at examples of hardware codecs driven by upstream drivers and their real-life applications, let us first think for a while about kinds or categories of codecs. So a video codec can do either of two things. I hope you can help me identifying this. So what do video codecs do? Either of two things. They decode. Bingo. What else? They encode. Thank you. Exactly. They encode and decode videos, but that's the easier categorization. They can do their job in either of two manners, and we can create a cross-product between these two categorizations to form a nice 2x2 matrix. So the other categorization is stateful versus stateless codecs. I talked about it last year in Prague. Long story short, a stateful codec keeps and maintains its encoding or decoding state in the hardware, while a stateless codec does not. And its encoding or decoding state needs to be kept and maintained elsewhere. This has consequences. For example, when you want to decode a frame from another sequence and then resume the original sequence with a stateful codec, the codec needs to recreate the state it was in when it saw the original sequence, which might require reprocessing several frames or maybe even an entire group of pictures. Whereas a stateless codec just processes the next frame using whatever the state it is pointed at. On a flip side, users of stateless codecs need to provide a lot of parameters on top of a subset of a bit stream, for example, part of which they also need to parse themselves. The trend is generally towards stateless codecs, though. You can notice that one tick mark is missing. You will learn later in this talk why it is so. And now let us see examples of several codecs. These are example domains where you can find hardware video codecs driven by upstream drivers, some of which are listed in the following slide. This is a non-exhaustive list in no particular order. So there is Coda, which is used by Safran, former Zodiac, in aircraft infotainment, or by Bosch in car infotainment, or by AgBrain in farm tractors. There's Venus from Qualcomm, which has been used in Chrome OS and Android devices. Wave 5 from Chips and Media, found in TI chips, which is automotive-oriented. MFC from Samsung, and that is exactly the codec I was talking about in the beginning of this talk. It's been used in Android devices. There was a Chromebook with an Exynos chip and a number of development boards from a company called Hardkernel. Tegra is an old-ish codec from NVIDIA, which has found its interesting niche in drones. Then there's RKV-DEC and RKV-ENC from Rockchip, which is used in set-top or media boxes. And then there's Hantro, also known as VeriSilicon, which, when part of an IMX.8 from NXP, is used in automotive. Safran uses it in infotainment, Blaze in AI, Intel Movidius for augmented reality, STMicro in their STM32MP25 chip, Microchip in their SAM-A5D4 chip, and there's VENC and VDEC from MediaTek used in Chrome OS devices. So let us recap what we have seen so far. A codec is either a specification or its implementation in software or in hardware. Growing efficiency implies growing complexity, which increases demand for hardware acceleration. To take advantage of hardware acceleration, drivers must exist. There are stateful and stateless encoders and decoders. We have seen example uses of codecs driven by upstream drivers. Now, let us move on to a bit of history. I don't know if you have seen the movie The Holdovers, The history teacher in this film says a great sentence. You see, history is not simply the study of the past. It's an explanation of the present. I cannot imagine a better way to encourage you to listen to some explanation of the present of hardware codecs support in Linux. If this were a date, then the computers, the way we know them, did not exist yet. The transistor would not be invented until 1947. But 3 Polish mathematicians, Rejewski, Różycki, and Zygalski, had cracked the enigma 3 years before. The Germans kept improving the system, and at some point, the Polish started lacking resources to keep up, so they passed the results to the British, who at Bletchley Park continued where the Polish left off, and then the Colossus was created, except that this number is actually a kernel release, which happened around 2010. My colleagues at Samsung R&D Center in Warsaw, Poland, Paweł Ościak and Marek Szyprowski, contributed mem-to-mem framework. It was meant for devices which are both output and capture. If you are not into video for Linux, then this naming might be a bit confusing to you because perhaps you would want source and destination instead. To understand these names better, you need to move 25 years back in time when video for Linux was started. A popular kind of hardware at that time was an analog TV grabber card, which received analog TV signal, tuned to a particular frequency, and kept digitalizing received frames and passing this data to a computer. Such a device was capturing the frames, hence its class name. There were, of course, devices doing the converse, which were transferring the data in the opposite direction, from a computer to the hardware in order to output it. And mem-to-mem framework was meant for devices doing the two at the same time, transferring data to the hardware and receiving processed data, because nothing like that had existed before in Video for Linux 2. It had to be decided how this is arranged, what happens when an interrupt is received, how to coordinate between the two video queues, and so on. According to the commit message, the mem-to-mem was meant for devices such as resizers, rotators, or color space converters. No mention of video codecs. It was later that same year that the subsystem patches started being tagged media rather than v4l/dvb. Early the following year, at kernel release 2.6.39, which, by the way, was the last kernel release of the 2.6 series and the last using 3-number versioning. The following revision was 3.0. The same two guys upstream VideoBuff2, a successor to VideoBuff. It was meant as an intermediate layer between user space applications and device drivers, also providing low-level modular memory management function for drivers. It was a set of functionality that all Video for Linux 2 drivers would have to otherwise keep reproducing. So VideoBuff2 defines planes. For example, a color component of a video frame can be stored in its own plane. VideoBuff2 abstracts the memory plane data is allocated from. It was either memory mapped memory or user pointer memory, which is allocated by the user, and then the user passes the pointer to it via the UAPI. Later, DMA buff support was added. A VideoBuff2 buffer consists of several such planes, and buffers are stored in a VideoBuff2 queue. VideoBuff2 also keeps track of each buffer state, so that, for example, the CPU does not attempt to modify the buffer while it is owned by the hardware, or vice versa. Another colleague from the same team, Kamil Dębski, in late 2011, at kernel 3.1, upstreamed the very first Video for Linux 2 video codec driver for the MFC, multifunction codec, found in Samsung chips. Initial support was for S5P v210 and Exynos 4. By the way, the driver featured stateful H.264 encoder and decoder, and at that time, there was no distinction between stateful and stateless. because only stateful hardware existed. Seeing the history in perspective, we now use this kind of codec classification. Again, history being explanation of the present. The driver used and uses to this day the mem-to-mem and the video buff2 frameworks. Note how the former, despite its commit message, turns out suitable for something more than resizers, rotators, or color space converters. The context of all these contributions was Chrome OS team partnering with Samsung and Asus to create the first ARM Chromebook. I want to mention another driver, not because it's a terribly important driver, but because it's important to me. Because I contributed it. It was a driver for a JPEG codec found in the same chips as the above mentioned MFC, and I upstreamed it in early 2012 at kernel 3.3. Later that year, a very important moment happens. A video codec driver from another vendor lands upstream in 3.7. It was from Javier Martin, writing software for chips and media. The driver was for Coda, and it featured stateful MPEG-4 and H.264 encoders. From this moment on, the upstream support of hardware video codecs has not been a Samsung monoculture. However, the start of this era was not great. You would expect user space written with MFC in mind, working correctly with Coda, but there were some problems. For example, in how the two mark end of stream MFC raises an interrupt while Coda signals with the last frame. Obviously, something had to be done. At LinuxCon Europe 2012 in Barcelona, Spain, talks started and continued until ELC 2014 in Düsseldorf, Germany. This resulted in a de facto stateful codec UAPI which was later implemented in already existing MFC and Coda. But it was not until 2019 and 2020 when stateful decoders and encoders specifications were merged upstream. They were merged by Tomasz Figa, who originally was the member of the same team that upstreamed mem-to-mem, video buff2, or the first video codec driver. However, at the time of spec submission, Tomasz was affiliated at chromium.org. You can see that it takes time to settle on what the spec and the UAPI should be. First, it takes some considerable amount of thought, and then it also takes the maintainers to become confident that what you want to merge is the right thing. Having that experience in mind, with stateless codecs, the community has been smarter, and this time we started with stateless decoders UAPI before merging the drivers. Only this time the process was more difficult because unlike stateful decoders, which are fed compressed bitstream and figure everything out internally, stateless decoders need to be passed a lot of parameters, found, for example, in frame headers, such as SPS, sequence parameter set, or PPS, picture parameter set. The UAPI should be broad enough to, at the very least, cover all decoders available at specification release time, and this required a detailed study of available decoders and resulted both in UAPI controls and stateless decoder specification in upstream Linux, which was merged in 2019 by Alexandre Courbeau, affiliated at chromium.org. The context this time was Chrome OS team working on second generation ARM Chromebook. And in the meantime, in 2018, Hans Verkuy upstreamed request API in 4.20, which, by the way, was the last kernel release from the 4.something series. To understand requests better, let's think for a while about an old-style output device which receives frames from computer memory and generates a signal suitable for broadcasting. Let's suppose there is some control in the device, not necessarily a physical knob, but some hardware setting controllable from the software. The control is maybe used to set the brightness or contrast or saturation in the generated signal. If frames A and B have been emitted, and from frame C on, you want this parameter changed, the control needs to be changed. But think what happens if we want this control setting applied for each frame separately. We need to wait until the previous frame is done, but before the next one is started, then apply the setting, then refrain from changing it until the current frame is done. And this is exactly the problem which requests in Video for Linux to solve. They offer you a framework to apply control settings for each frame separately and not have to worry about the above-mentioned timing issues. The fundamental concept in that framework is a request object which is created per each frame. In video codecs, requests are useful for associating an output buffer, and by now you already know what output means in this context. Associating an output buffer with a set of controls to be applied when processing a particular frame. And in stateless codecs, there's a lot of parameters to be associated with a frame. Now, given the existing work on stateless codec spec and this requests API, in 2018, at the same kernel release, Paul Kociałkowski from Butlin upstreamed a driver for Sidros, also known as Video Engine, in all Winner chips. It featured a stateless MPEG-2 decoder. An interesting fact is that this effort was crowdfunded on Kickstarter. Another interesting fact is that the relevant UAPI was moved from public headers to staging soon after merging the driver, but before 4.20 was released. It turned out not stable enough, but keeping it in staging allowed working on it until it becomes good enough to be destaged. On a flip side, the concept of a staging UAPI can also backfire a bit, because if it's not an official Linux UAPI, then people might be reluctant to use it. And how do you make this UAPI mature enough to be fully merged upstream? By having people use it, which creates a chicken and egg dilemma. You will hear more about how we intend to solve it the next time it happens in the part of this talk about the future. So here we are in 2024. I am not mentioning other codecs history, not because I consider them unimportant, but once the spec is merged, adding a new driver is usually just following the existing example, unless the hardware is unique, which can of course happen. There are about 10 video codec drivers, plus a couple of them in staging, some of the drivers supporting numerous variants of the hardware, so it is a safe bet to say that tens of hardware kinds are supported upstream. What if you wanted to contribute a new codec driver? When submitting a codec driver upstream, you should, as always, provide V4L2 compliance report. For decoders, you should include a Fluster score. Fluster is an open source tool used to test decoders' compliance. We ask you to run Fluster and to document the failures, if any. Later on, we just ask to report if the score moved or stayed the same to see if there are no regressions. For encoders, there is no suitable tool yet. Of course, as part of your submission, it would be really nice if the driver you submit worked. Enough history and present, let's now try predicting the future. Talking about the future, we need to look at two horizons. There is pending work, which is expected to be upstreamed soon-ish, the order of months or 1-2 years, and there is more distant future, 5 to 10 years from now. Let us first look at the pending work. You remember that the 2x2 matrix in the beginning of this talk was missing one tick mark. It was for stateless encoders, which are still missing. I mean, the hardware does exist, but there is no support in the upstream kernel yet. An additional difficulty to add this support is that in modern codecs, the spec says only what a valid bit stream must conform to and how to decode it, but it says little to nothing about how to come up with a valid bit stream. Last year I posted an RFC for a stateless VP8 encoder. Later, last year, STMicro, in cooperation with Collabra, posted an RFC for an H.264 stateless encoder. So there are already two RFC quality stateless encoder drivers, but the stateless encoder spec is still missing upstream. Now, this is where we come back to the chicken and egg dilemma of a so-called staging UAPI. The staging UAPI was good when stateless decoders were being specified, because at that time we, the community, were learning about stateless codecs. Now that we do have experience and do know about stateless codecs, it seems a better approach is to merge the UAPI directly to avoid the said chicken and egg dilemma. VNAS replacement. VNAS is actually the name of the firmware. Its replacement will be called Iris and will run on the same hardware. The intention is to have a new driver, and for the two drivers, the old and the new, to coexist for some time. It is likely that the new driver will not use the mem-to-mem framework. Raspberry Pi. So far, Raspberry Pi is or has generally been open source, but not necessarily upstream. There is a work by a volunteer to merge the Raspberry Pi codec support upstream. The codec is called MMAL, and it features H.264 and MJPEG encoders and decoders, MPEG-4 and H.263 and VP8 decoders, and provided a license fee has been paid, an MPEG-2 decoder. I don't know how this relates to MPEG-2 patents expiring last January. Chips and media. We can expect new Wave 5 features. 4:2 subsampling support, 10-bit support, HEVC high profile support, and perhaps some new encoder controls. Notably, ROI, region of interest, is missing. And who knows, maybe Wave 6 will come to be. So that's the pending work on codec drivers. Not so difficult to predict because there are patches circulating already. Let's try predicting the not so distant future. We can expect an 8K driver for RK3588. And for a bit older RK3399, we can expect an encoder and decoder. By the way, in this latter chip, there are two sets of codecs. Hunter, also known as VeriSilicon, and that generally has drivers upstream, and Rockchip's own RKV-Enc and RKV-Dec. Codec conformance tests. For decoders, we already have conformance tests with Fluster. So if new codec specs appear, we will likely see new test classes and new test vectors added to Fluster. With encoders, we would love to have a conformance test tool, but that's a trickier case than with decoders, because in modern codecs, understood as specifications, encoders are not specified. So while with decoders there's only a single possible way a given bit stream should be decompressed, with encoders, multiple variants of a valid bit stream are possible, which means that there are multiple potentially different yet visually correct decompressed variants of the original video being encoded, which means that there is no single expected result, so there is no easy way to automate this process. Maybe we can have some heuristic assessment of how close to or how far from the original video an encoded and then decoded video is, and then have a threshold to decide whether the encoding result is good enough. The following predictions will be for the distant future. Mem-to-mem. It dates back to a historic kernel release from 14 years ago. Just to set this in context, in 2010, iPhone 4 and Galaxy S, just S, no number, were released, so pretty long time ago. What served well the very first upstream codec, which was MFC from Samsung, will not necessarily serve well all other codecs. And indeed, not all memory-to-memory drivers use mem-to-mem framework. A legitimate concern is how to support multi-core codecs, where cores can be, for example, bound together to handle larger resolutions, or they can be used to do entropy decoding and frame reconstruction in parallel to speed up the process. So we might see something being created. On the other hand, challenging an existing status quo is easier said than done, so we will see. And very distant future, convergence of stateless and DRM. It turns out that the workflow of using GPUs in DRM is similar to the workflow of using stateless codecs in Video for Linux too. So who knows, maybe in some distant future we will see stateless codecs migrating to DRM, who knows. Then there is also Vulkan Video. We don't know how it will relate to future kernel APIs. So let's summarize. You have learned what video codecs are, a spec or an implementation. You've seen what categories of codecs there are, and you have seen examples of codecs driven by upstream drivers in real-life applications. You then learned about the key points in codec support history in upstream Linux kernel, and then we tried predicting the future. That concludes my presentation. Are there any questions? There's a mic for you. Yeah.
So I was curious to know why we need an encoder spec, because if I have used my encoder and generated the bit stream, and if I use a standard decoder like as provided by the spec ITU or one, and if it's able to decode that stream, then isn't my encoded stream good enough, and it indirectly proves that encoder is good?
So the question is, why do we need a spec, a specification in the...
For the encoder, because if encoded stream is, the decoder is able to decode the encoded stream correctly without any errors, then it indirectly tells that encoder did the job correctly.
So we should not confuse two things. In codecs specifications such as H.264, for example, AV1 or whatever, the encoders are not specified indeed. But in the Linux kernel, we need to know what a stateless encoder is, what kind of controls there are or there should be to control such a codec. And that's the kind of specification I was talking about.
Sorry, I was talking about that similar to Fluster, like the test specification or the test framework. Like for decoder, you said we need Fluster compliance. For the encoder, is it okay? Like if I pass the encoded stream to the decoder and run the Fluster compliance with that?
Yeah, that's basically correct what you are saying. Once the stream decodes correctly, it means that the encoded stream is correct. But on the other hand, if we don't have someone look at the actual contents, then perhaps the stream is syntactically correct, but the contents is corrupted. Right? So that is why we would like to have some tool that verifies that the contents is actually visually correct. But as you are saying, it is enough to pass an encoded bit stream to a decoder, and if a compliant decoder can decode it, that means that the encoder did its job well.
Thanks.
Thank you. Any other question?
Not sure I missed it, or maybe you didn't mention, but what are the reasons M2M is not suitable for modern needs?
I wouldn't say it's not suitable for modern needs, but it might be not suitable for some modern codecs, which are, for example, multi-core codecs, and they can do their job in parallel. For example, they can do entropy decoding and reconstructing a frame at the same time. And the reason is that originally mem-to-mem creators simply did not envision such a scenario. But again, it was 14 years ago, right? So.
Sure. Thank you.
Thank you. Any other questions?
Thanks for the thanks for the talk. I was just wondering if you knew the status of like user space libraries of using stateful, stateless, and requests like FFmpeg or GStreamer.
They do. They do support it.
Fully or up?
Yeah, I mean, to merge a driver upstream or UAPI upstream, I'm talking about the Linux kernel, you need user space users, right? So a prerequisite, a must-have condition is to have some user space using it, and the go-to user space is GStreamer or FFmpeg. So they do support stateless and requests.
Okay, thank you.
Any other questions?
I just wonder why the stateless codec become a trend. Do you have any idea for it?
Well, it's probably difficult to say whether stateful or stateless is better. It's like asking tea or coffee. Yes. Probably depends on the application, but it seems that stateless are more versatile because you can easily handle several streams at the same time. While with stateless, if the state is built into the codec, then if you need to change that state, the hardware needs to, recreate the state. So I guess that's one of the reasons. The other reason is that I would say with modern CPUs, parsing a bit of a bit stream in decoders is not a real problem. But what really needs support is the inverse DCT transform, quantization and so, or dequantization and so on. And that's where hardware assistance really comes in handy. So I would say these are the reasons why stateless codecs are becoming maybe more popular. Yeah.
Okay, thank you.
Thank you.
The stateless codecs are lesser area in the hardware, so the hardware is simple and it kind of saves area in the SoC. So that could be.
It could be you trade, the amount of software support needed to run your hardware codec against the amount of transistors. Right. So that could be also a reason. Yes. Any other questions?
I will ask one more.
Yep.
So I was kind of transitioning from OMX API to V4L2 for the codecs, and I see like some of the controls are missing. Like for example, if I have to pass an SCI UDU message to the codec or something, then I couldn't find any specific S control or ext control for that.
So you are transitioning from other API to V4L2?
So I had used OpenMax API for it. So there we had some OMX extensions for these kind of things, like SCI prefix and all. But the V4L2 API, I could not find how to pass the SCI information using the v4L2 API to the codec and that. So
what can we do? You're invited to provide
yeah.
support.
So is like maybe is it okay to propose those as controls like that, or?
I mean, it's open source. You can propose anything as long as you have good arguments.
Mm-hmm.
The next occasion to do it is the Media Summit, which will be held somewhere in the autumn.
Austria, yeah. Also, like this spec is kind of tight. The v4L2 spec for the codec is kind of dependent on the v4L2 spec for capture, because let's say I'm using capture to encode, and if the capture the resolution changes, then they kind of need to be in sync with each other. So those also I was not able to find exact spec on how to handle these kind of use cases in sync with the capture and the codec. So.
And what the question is?
So let's say I'm encoding a stream and there's a resolution change, like
Mm-hmm.
I'm changing the camera resolution from 1080p to 480p. Then how do I handle this state using the v4L2 API?
Okay, so recently a new feature was merged, which is remove buffs, I think, and its purpose is exactly handling resolution change. So you might want to have a look at the remove buff IOCTL, which was added just recently.
Okay, thank you.
Thank you. Any other questions? If no questions, then thanks for coming. Thank you. Nice. I had to compete with Tim Baird, so.
Yeah. And there were mentions to us there as well. He had a full slide about the GitLab stuff. On the talk. Yesterday I had to compete with Linux. Not too many places.
I set up mostly myself, except the mic.
Someone came and helped you?
Yes, but actually the mic is here, so. And pro tip, I heard from my colleague, if your laptop does not notice the projector, you need to reboot while the HDMI cable is connected.
Is that the only option they have? It's HDMI, no Type-C?
Just HDMI.
That's not going to be a problem. I'm using Windows, so I hope it's okay.
Oops.
don't mind, could take a picture and just share it with me later.
Yeah, I will take the picture. On Devash. Yeah. Thanks for the talk and reviewing the patches and all. So you remember like that JPEG discussion. So you had suggested to make a JPEG library. So I'm working on that. So I had sent the imagination JPEG code to that, and then Andrew and others also using the same JPEG headers and all. But I think we can have whatever example is there in the spec, those example tables we can use. So is it okay to have that and equal to JPEG also, the API function? Yeah, I'll try to send it the patch and see if it works.
Do you have any audio in your presentation?
No.
Okay. This will go on. There's an on-off switch there when you're ready. Do you want to test it?
Hello? Yeah, it works. Thanks.
And then if you use this for Q&A, there's an on-off switch right.
Hello. So it's 9:55. I guess I'll get started. Good morning, everyone, and welcome to Embedded Open Source Summit. Today I'm going to be speaking about camera and ISP drivers using the V4L2 media controller framework. So I think oftentimes many people are very familiar with V4L2 because of its age, but not everyone is very sure about what media controller framework is. And if that's your question, I think you're at the right place. That's what I'm going to be talking about today. I won't be covering a lot of V4L2 as such, but mostly talking about the media controller framework aspect of it and how it's very suitable to build camera and ISP drivers. So that's going to be my focus for the talk today. So let's first start and look at the evolution of cameras in general to understand that why this transition from V4L2 to V4L2 media controller happened, right? So in the early or mid 2000s, cameras were mostly built with using external ISPs. ISP stands for image signal processor, and it's usually the processor that does some basic signal correction for raw image sensors to make it produce images that can be viewed by, by humans, right? So the external ISPs back in that time were either based off USB cameras, which were based on the UVC protocols. That means the USB camera had a built-in external ISP in there. There were other instances of external modules that were built with parallel camera interfaces because that was that MIPI-based camera serial interfaces weren't out at that point. And then you had CSI and CSI2 based camera interfaces. So that was kind of what, like until mid 2000s, this is kind of what was available. Then things started getting interesting. SoC started including ISPs inside of them, right? And this was purely a cost-driven approach because, cost of transistors and stuff started going low. So SoC started now putting the ISPs in there, which used to earlier be external, right? And I think this trend started with OMAP3 and soon to follow Qualcomm. And these days, most SoCs have some sort of ISPs built inside of them. So let's take a quick look at what external ISPs looks like. So I've drawn a dashed red line, which shows the API abstraction layer. And then in any camera, right, you'd always have a raw image sensor, and these are typically bare. Bare is a specific pattern which is used to capture light using the image sensor array. And the basic idea here is that there's twice the amount of green pixels as compared to red and blue. And one of the jobs of the ISP is to correct for this and then actually produce a red, green, and blue pixel for every pixel, right? And so this bare sensor is typically over some sort of an interface, some kind of camera capture interface. The data is fed into an external ISP, and that ISP basically corrects for one of these things, like I said, debaring, and then it does a lot of other image processing activities, and then finally the processed image is sent out via another camera capture interface to the SoC or host PC in this case, right? And this was the API abstraction layer because the hardware was largely external, so Linux software had to deal with this camera interface and all of this. So V4L2 was really suitable for this, and that's what a normal V4L2 camera stack would look like. So you'd have hardware at the bottom layer, you'd have a V4L2 driver, and then finally you'll have a V4L2 application around here, right? And then the flow of the application would look like this. You'd first start with querying capabilities, querying your camera. You'd set up formats, you'd request buffers, query buffers, then you'd start queuing buffers, and then you do a state change and you change the state of the camera to stream on. And after that, it's a constant loop of dequeuing, consuming those buffers and then queuing them back. And that loop continues for as long as you're streaming. And when the intent to stream goes away, you call a stop stream API. So this was the typical V4L2 application flow. However, let's take a look how things change with internal ISPs. You still have the same bare raw sensor external, right? But then through the camera capture interface, now the frames go into an ISP, which is now contained inside of that of an SoC or host PC, right? So what's basically happened is the API abstraction layer has moved right now. Now you certainly need to worry about managing this ISP within Linux, right? And So let's now see, just like how we saw the evolution of cameras, we have to also look at the evolution of V4L2, right? So with external ISPs, V4L2 was, the old V4L2 was pretty good for this. So it provided APIs that allowed to view a camera as a whole, right? And you could view a camera as a collection of various controls and usually a single image or a video stream, right? That was the normal level of abstraction, and V4L2 was pretty good for this. But with internal ISPs, now only the bare sensor is there externally. ISPs are now contained inside the SoC. Complexity has grown many-fold. As these ISPs are fairly complex, they could have various different architectures, right? And to support this is what media controller framework was added. And it actually just augments V4L2 to help deal with just such complexities, right? So it's not changing V4L2 very much, but just adding stuff on top of it to make it more friendly for ISP-like devices. There are other uses for media controller like DVBs, but which I'm not going to be covering, but I'm only covering the ISP aspects of it. So for the rest of the presentation, we need to take some sort of an example ISP. So this is a very, very generic ISP. It's not a real one. It's just a mock kind of an ISP, but many of the ISPs should contain similar blocks. So, you know, as usual, you do have a external bare image sensor, and you do have an I2C controller many times to talk to this image sensor over the I2C bus, and you could basically configure it, change states, you know, do various controls like exposure, gain, or whatever special controls that particular image sensor might have. You do have a CSI2 interface through which the image stream enters into the first block inside the SoC, which is typically known as the CSI2 controller, or it's also known as the CSI2 RX because it's the receiver of the frames, right? And there are other interfaces too. You can still have parallel interfaces, though for many years CSI2 has been the de facto standard on top of D-Phi. There are other PHY protocols that are being associated with CSI, like the C-Phi, but the most common image sensors out there, the most popular ones are CSI2 and D-Phi combination, like I've shown here, right? And once the job of this block is to take the serial the image stream over the serial interface and convert it into some sort of a bus-based image feed to the rest of the ISP, so that the ISP can inline process these pixels and do various signal corrections to it, right? So this is a very simple ISP. So the first stage here is a black level correction. So that basically removes for you know, all the different analog gains that the image sensor has that needs to be corrected so that a black looks like a black. And that's the block. That's the job of this block, and it's typically determined through some sort of calibration process, which is stored on some non-volatile memory, and then you kind of apply that correction on a frame-by-frame basis, and you do modify them when your gains change. So then there's a defective pixel correction. Now this is done because during the sensor manufacturing process, oftentimes there are dead pixels or defective pixels, and you do need some sort of a block inside an ISP to correct for those. So that's the basic job of this block. Now the next block is a demosaic. So that's basically the block that's going to change the bare pattern into RGB typically, but it could also convert it to YUV. But most demosaic blocks will change it into an RGB format. Following that could be like a color space correction. You know, this is just to make the image look better, more appealing to humans, right? And then following that, there could be like a scaling or further color space conversion blocks, right? And then there's typically a DMA at the end of it, just to write out the frames out to DDR memory. So there's a DMA block there. Most ISPs will also have some sort of statistics blocks, which will be tapped at somewhere in the pipeline, typically before the demosaic, but there are cases where it could be after the demosaic as well. And those statistics can also get written out to DDR. And the reason for these statistics is so that there's a runtime aspect of an ISP, which is typically known as the 3A algorithms, and the 3A stands for autofocus, auto white balance, and auto exposure. And these algorithms are looking at hardware statistics produced by the ISP hardware, and they're on the fly making adjustments and, you know, making the image always look better. This is particularly needed for any preview or video based usage of an ISP, even for snapshot as such, because you first run a preview and make sure that the preview looks good, and then take a picture, right? So it's very essential for good image quality. So that's basically a quick run of this very simple generic ISP. So now let's talk a little bit about media controller. Like I've introduced the problem statement before, that ISPs have multiple processing blocks, so they can be connected to form processing pipelines or graph, like the way we saw in the previous diagram. So media controller actually allows to represent such processing blocks using media device model. Now what's a media device model? So media device model consists of these following objects. So there's something called as a media entity. That is a basic media hardware or software processing block. A media pad is a connection pad that allows connecting one entity to another via links. So each entity would have at least one or more pads normally. And then there's a media link, and these are the connection between these pads. So these links could further be like, interface link that's between a Linux kernel interface and an entity. A data link is purely between two pads and an entity. Two pads, in two different entities. And ancillary link, this is some sort of a logical link between two entities. So the normal devices that fall into this category are lens actuator for the autofocus and flash devices. So here's a simple diagram of media device model explained. And we have three entities here. We have entity A, entity B, and entity C. So the black arrows that you see are the media links, like we saw from the previous slide. And these are the media pads. Now, entity C looks like it doesn't have a media pad, but this is a special kind of an entity that has an implicit pad, basically. So because you can always connect to it. That's why it's not shown here, but it does have an implicit pad. Now let's take a look at relationship between a media device and V4L2, right? The same diagram. You have the three entities. The green blocks, right, in this diagram are often known as V4L2 subdevice entities. So you can roughly think of them as they are participating in the ISP pipeline. They do produce data, but not directly to DDR for the most part, right? But the data flows from one entity to the other, whereas the yellow blocks that you see in the media pipeline graphs are video device entities, and these typically either write out or read, in some cases, image data via some sort of a DMA. So rough mental model is green block means it's mostly controls, a bunch of different controls. Data is still flowing through it. You can stream on and stream off, but you don't directly pull image data out of it. But if you see a yellow block, then it also may have controls, but it'll most definitely have some sort of a DMA that writes out the image data or statistics data. So let's take a quick refresher on the same generic ISP. So you have all the different blocks. And now let's see how we can represent this as a media in the media device model. So this is a straightforward representation, which is one-to-one mapping. So everything you saw in the previous block diagram is now there here. And rightfully, all the control-only entities have been marked as green. And there's two DMAs, as you saw in the previous diagram. So they are video device entities. So there's one called the scaler here, and the other one is called the statistics. Now, arguably, you could simplify this a little bit. If all these three IPs are coming from the same, are authored by the same company, or coming from the same place, you could club them together and do a simplified pipeline diagram like this. So where you have an image sensor, CSI2, and this generic ISP that encapsulates the defective pixel correction, demosaic, as well as color correction, and then finally you have the same two output videos, which is the scaler and the statistics. So this is actually a decision to be made by the designer of the software for this ISP as to what kind of media and entity to actual pipeline relationships you want to do, and it also depends on what kind of controls or data flows out of it. So this is a decision process, but the media controller framework is very flexible and allows you to build different types of pipelines. So next important thing is to see the relationship between media controller and V4L2. So in this diagram, as you can see, the large red circle is the V4L2 device. So mental model here is that every ISP will be a single V4L2 device. That's the general understanding. And that device is going to contain multiple sub-devices, those green blocks that we saw in the previous diagram, and then a bunch of video devices, one or more. And these are represented inside the V4L2 device, the struct V4L2 device data structure, right? And now in each of these sub-devices and video devices, there is an embedded media entity object, right? And the relationship between these media entity objects are maintained by the media device data structure that's contained inside of the V4L2 device. And it basically, the V4L2 only sees all of this as a collection of various sub-devices and video devices, but media entity gives a ISP-like representation of it in the form of a graph, right? So it knows that this particular device is connected to the next one, and so it kind of represents the pipeline. So that's kind of what media entity does in addition. That's how it complements the V4L2 framework in allowing representation of such graphs. So now let's take a look at the media controller API in general and understand what are the different APIs available. I'm not going to be covering a lot of V4L2 APIs here. I'm just focusing mostly on the media controller aspect of it. So most devices, right, likely the core device that owns the ISP's V4L2 device structure is going to make this call. It's called the media device register. And it is often followed by an initialization call called media device init that sets up the media device object. And as a part of this call, you will see that a media device node also gets created. It's like dev media followed by some number. And the registration also sets some sort of file operations on this media device because it does support ioctl calls, which can be done on the user space. So user space, once it sees this /dev/media device node, like at least with this early stage of registration, you cannot query much, but once the device and all the sub-devices and video devices have registered, you're going to see there'll be a bunch of different ioctls that will allow you to query this device. You can look at the media device information. You can enumerate entities. You can enumerate the links. You could even set up links. So if you need to connect two pads together with a link, that such APIs are available. You could get the existing graph topology, so that lets you know what does the device look like. And finally, you could also allocate a media request. So that these are sort of the operations available here. A video sub device. So here, let's take a look at what all initializations for media controller are done by a video sub device. So here we're going to see that one of the core things is to initialize the media entities objects function. So there's an enum inside the kernel, so that allows you to classify your sub device as one of these, video composer, pixel formatter, encoder, converter, LUT, scaler, statistics, encoder, decoder, and ISP, right? The other thing you can do here is actually set up the number of pads, because as corresponding to the hardware, right? So you can set the pads. You can also decide which of these pads are source pads versus sync pads. And you can also indicate via flags if the pads cannot be, that they must be connected and can't be left dangling, which is typically true for hardwired ISPs when it's not very flexible. So hardware is only built one way, so you could put that flag and then actually enforce that connection. There are also a bunch of media entity operations that are available. So these are a few. One of them is firmware node pad. So this is normally used to determine pad number for async graph devices. I will cover this a little bit in a future slide. This link setup, so this is going to notify the entity about link changes. And then there's link validate. So this is where you can validate compatibility. So if user space tries to connect two pads, then those corresponding media entity object can validate and see if Can I accept the data format, resolution and things like that? So those sort of operations can be performed inside the link validate. So user space, it can scan the media pipeline, find subdev entities and discover the number of pads and whether they are source or sink. And they can also query the function of that entity. So if user space needs to make some decision based on what function this entity is providing, it can do that over here. So that's because whatever function got set over here is also queryable on the user space. So video device is pretty similar to that of a sub device. I think it's just implicitly has one pad in it. Think of it that way. And the same ops apply, the media ops, just like you saw on the previous slide. Even the function can be set over here. Let's take a look at some of the other APIs here. So there's APIs to set up link. So this is typically used in drivers to connect to media pads. And this is very true for hardwired ISPs that are not user changeable. Like data flows from this block to that, and that's not really very changeable inside the software, right? So in those cases, such links can be set up inside the driver itself. And only things that are flexible and changeable on the fly, you want to allow the user space to link with, right? There's APIs. This is not exhaustive. There's a lot more APIs. I just handpicked a few which were more interesting. Media entity find link. This can be used to find the link between two pads. Media entity remote pad unique or pad first. So this is used in the async graph subdevs, which I will cover in a moment. There's helpers to get the v4l to subdev from the media entity. So this is helpful when you're doing validate, for example, link validate. So you'd want to check the format currently set, right? And for that you need the v4l to subdev object. So this kind of a helper is here. Create ancillary link is used for lens and autofocus actuator subdevices. So user space, I think we mentioned this in the earlier slide. It can query the graph topology by calling the media IOCG topology. And this is often done with there is a utility in v4l utils package, which is called media-ctl, media CTL tool. It is a very good tool, and it's basically has a lot of this functionality that can be done in user space implemented as a part of that tool. It's a command line tool. So if you do a media CTL minus P, it's going to print out the existing graph topology. So you're going to see what's connected to what and whether they are connected, or what formats are, what are the default formats, and all those different details. I will share an example in the upcoming slides. And user space can also set up links, like I said, things that are not hardwired and connected. User space has an ability to go and link things together if it's allowed. And if the user space needs to do that, via a command line tool, it can use the same media CTL tool with the -- links command line option. So let's look at some of the pipeline APIs that media controller provides. So there's a media pipeline start. What this does is it starts the media pipeline, and it increments a start count member. So start count is mostly like a reference counting, so that you know that the media pipeline has started, and you keep ref counting it. So this is typically helpful for multi-stream video devices where you want to turn on the media pipeline once, and then as new streams get added to the application, you don't need to keep rerunning and restarting the pipeline. So this count can be monitored for those purposes. Media pipeline stops it, and it uses the start count until it goes down to 0. The pipeline is still kept active, and then when it goes to 0, that means no one needs this pipeline to be active. At that time, the pipeline would shut down. There are also other APIs to walk the graph. So there's media graph walk in it. It initializes the graph, and then there's a start. So you need to call this before doing a graph walk. And next is the media graph walk. Next is going to give you the next entity as you're walking the graph, right? And then finally there's a cleanup. So these 4 APIs are normally used together. And so these APIs are normally called from the main ISP the driver part that manages the entire ISP, and it is used for understanding and I mean, I think on the next slide I have some more details about it. So let's take a real example of the same pipeline that we had, right? We made sensor CSI to generic ISP with scalar and statistics. So one additional thing which is not a part of media controller, but it's still relevant here. It's just called the V4L2 async framework. So what happens is very often you'll find that these drivers, they are part of a single platform device. This could be a separate platform device. In some ISPs, they are part of the ISP, but sometimes it could be separated out. And the image sensor almost always is a different driver because that's under the I2C device driver path, right? So we need some mechanism for these two separate drivers, which are not really a part of the main ISP driver, to dynamically get added to this pipeline. So that is what V4L2 async framework does. So what it does is through device trees mechanisms, right? You can connect. It's called firmware node endpoint, and using that you can connect, a CSI2 and an image sensor through the device tree, and then these drivers, they're going to probe and register themselves independently. So these two drivers, the ones which are not a part of the main ISP yet, they are going to make a call, a function call called V4L2 subdevice async register. So that means it's doing an asynchronous registration. So if this driver comes first, it's going to asynchronously register itself, and if this driver comes later, it's going to notice that someone has tried to asynchronously register, and both of these drivers are going to get callbacks, which is called the bound callback. And in those bound callbacks, you can go and establish these links. So this gives a lot of flexibility because you may have different image sensors, and these are typically determined by the board you're working on. So async framework is very essential to get a fully functional pipeline. You don't have to put everything into a giant monolithic driver. You can keep things separate, and they can be completely different drivers, and with the help of async framework, they can connect with each other. So that's very interesting, and it allows to keep things very modular. So you could have one image sensor driver that works with multiple ISPs, right? Or you could have a CSI2 driver that can also work with multiple ISPs. So there's a lot of flexibility in doing it this way. So once all the entities are registered, and you've had the bound callbacks, and then you had there's also a callback called complete, which normally happens on the root ISP driver, and what that tells is that all your entities, via async framework, have all registered and it's all done. So at this point, the driver can go and really do the finalization of the media pipeline. So that's what the intent of that callback is. So once all of these entities are registered, you do a stream on either one of these. So applications can, either start off with streaming on the scalar or the statistics. And at this point, you'd use those media pipeline APIs to walk the graph, right? And normally the way you do it is you stream on the entity first, and then you just go upstream. You stream on this, then you stream on this, and then you stream on this. And then you take a look at the start count, and it's already incremented, and especially when you're streaming on the next video device, the statistics. At that point you say, what, the ISP is already running, I just turn on the statistics alone. And then when you're streaming off, it goes the reverse way, right? You first stream off the image sensor, then this, and then finally these device nodes. And then the last device, video device that streams off is the one which is actually going to stream off the ISP. So here's an example of the media CTL tool, right? So this is, I think it's a little too small, but I was trying to fit it all in one slide. So you can use the media CTL. This is an example from the Rockchip ISP, which is I think present in RK3399. So if you run this command, media CTL -d, and give the name of the media device and give -p, it's going to give this this kind of an output. So you are going to see the name of the driver, the model of the driver, and all of these different fields that the driver sets, right? And then the next thing is the output of the G topology, the one we spoke about earlier. And you do see all the different entities here. So there is a mapping here. So you do see how many pads are there here. For example, entity 1, that is the ISP subdev, which corresponds to this particular guy over here. It shows that it has 4 pads, right? And there are 2 input pads and there's 2 output pads. Then from one of the output pads, right, the number 2, the video goes to 2 output paths, right? Two subdevs. One of them is called a main path and a self path. And those have like, you know, these are like, I think they are like scalars and other post-processing blocks. And from here, you go down to some video devices which have DMA capability of writing out the video stream. So you also notice that there is a pad here, 3, from which statistics is pulled out. So there is like a statistics video buffer. And then interestingly, the Rockchip guys have done like a virtual video device node, something of that sort, and they use this for the parameters. I mean, normally parameters are done via V4L control, but they have chosen to do it using a video buffer. So a video buffer is a parameter buffer which goes and configures parts of the pipeline. And then there's this image sensor here. So in this particular case, in this particular example of RK ISP1, this entity registered asynchronously using the V4L2 async framework. The rest of the ISPs registered itself. And then when the bound callbacks and complete callback happened, this link was established. And this image sensor became a part of this media pipeline. So there is something called a media request API, which I actually thought that it needs a session of its own, so I'm not going to be covering it here. It's not related to the graphs and other things, but it's related to, you know, like the Android HAL3 style requests and metadata. So it's more on supporting that. So I'll perhaps do another session next ELC to cover this in more detail. Here are some of the references. I think I finished about 3 minutes early, so yeah, if you have more time for questions. So any questions?
So I'm curious to know, how do we control the resume sequence? Like, for example, if you're starting the camera, then we have this V4L2 async that has that bound notification, and then we can stream on in the order that you said, right? ISP first and from last to first.
Yeah.
But if we are like suspending the device and resuming back, how do we control that same flow? Like,
oh, so you mean to say the power management suspend resume?
Yes.
Is that the one? Yeah, so typically, actually I don't know the right way, but what I would do would monitor the start count. That's an indication that the pipeline is active, and any attempt to suspend while the start count is not 0 must be rejected, saying that, you know, you cannot suspend the ISP at this point. It might be possible, but it's very difficult to go and save the state of a running ISP and then restore it exactly from that point, right? But you'd normally want to suspend when nothing is running, right? You know, or the pipeline start count is 0.
yeah, that's fine. I think when we are looking, we could not find any way to control the sequence of resuming. Like for resuming, we want to, you know, start the ISP first and then the CSI and at last the image sensor.
Or resume. So at least in my experience, I know there may be a way to do it. In my experience, for ISP suspend resume use cases, right, are normally user space initiated. You do have to tell the application to close the streams and then go to suspend. And then, you know, because those callbacks can also go to the application side through some middleware frameworks. It's very, very challenging to, I'm not saying it's impossible, it's challenging, and I have not seen any examples of ISPs, but in my scope of things I've looked at. So.
Like for example, how can I control from the bridge driver to say like not to probe the image sensor until it has powered on? Like for example, for startup we have this bound callback and all, but for the reverse, like on the resume path, is there like from the bridge driver how we can control the image sensor to not power on the sensor until the rest of the pipeline is up?
Yeah, so the bridge driver can do that. Yes, it can do that. Yes.
Okay,
So
thanks.
basically, that's the purpose of the media API. No, graph traversal one is just to understand that you will realize that image sensor is at the source of the pipeline, right? So through that, you know that it needs to be powered on at the end, right? And once you get the handle of its V4L to sub device, you can make stream on calls. You can make even S power calls to control that sequence. So the main owner or the bridge driver, like you mentioned, can decide that and control it.
Thank you.
Any other questions? Okay, if there's no questions, I think we learned 5 minutes early. Thanks a lot for joining this talk, everyone. Oh, okay, thank you. Thanks. Yeah, you can share this if you want to. Yeah, hi. Sure. So, no, the thing is that ISP is a capture device, so there is no input buffer. That is actually real world capture. There's only like a capture buffer that gets on the output. Oh no, different buffers. So each of them is a different video device. You need to do like the second slide I had, right, where you have V4L2 query browse, everything you need to do, but you need to perform that on all the yellow blocks. So each of them is a separate video device. And the media controller just lets you view them that way, they're all related, they're not unrelated. It brings them together. Maybe I should open the diagram for it might help you. It might help with the discussion. Yeah. It is a buffer, but it is not like a conventional video buffer. It will be of that statistics. There is a thing called metadata buffer format. It follows that topically because every ISP will have different. There is no standardization on that, right? Every ISP will have their own statistic format and descriptions. So your application first using media controller will find out, okay, it's a complex ISP. There's lots of things. It will identify all these parts, and then it knows there are 2 video devices. This is simple. This very because the rock chip is also more complex and and you could even like dynamically change paths. Some ISPs allow for that as well. Right? The framework itself makes no assumptions. It lets you do all of the above, right? That is the old style. OMAP 3 uses it that way, right? But I think OMAP 3 is a little bit dated driver. I think the newer ones are using it as a video device. Because events is yet another odd thing, right? You have to do subscribe and all that. So they just it's doable. I mean, there's no rules here. You can do that too. But I think the newer drivers tend to use it as a video device. And you saw the rock chip. They're using a video buffer as a parameter buffer, which I thought was pretty unique. Yeah, I think the reason why they did it, I don't know. I have not worked with them. I'm usually observing it from outside. I think they were trying to avoid writing thousands of controls. It's just easier as a buffer. Also, it makes it zero copy by that sense. The buffer is managed by DB2. Yeah, exactly. They pass some predefined structure and they use the same structure in application also. Right. Sure, yeah. Also, I can give you my phone number if possible. You are on WhatsApp?
It all started off with this problem. I have done some NPI projects internally, but some rest of the stuff is confidential, so I can't talk about it yet. But yeah, we are doing something related. Not some of your stuff is research in nature. We do lots of things. Probably some of it comes out as production. Some of them use RTOS. Those RTOS are all hash values. So, hello everyone. Thank you for attending my talk of all the talks. So, if you haven't met me yet, my name is Brian. I work for TI's Baseport team. I primarily focus on the bootloaders and everything below the kernel, essentially. Pekka Varas is also a member of our senior technical staff. He does a lot of work with the real-time Linux kernels. Unfortunately, he can't be with us. He travels way too much, and so he had to make some calls. But anyway, he is kind of the big muscle behind all this. Before I begin, I wanted to thank TI. I am very fortunate to work with a company that understands like true open source and not just like how to put that on like marketing material. It allows me to attend these conferences and do everything I get to do here. One more thing is I am very good at getting myself into trouble, so please don't use anything in here to get me in trouble, because I do it all the time. All right, so the very beginning. You've got a new project, a great idea, right? You start collecting all your requirements before you make any hardware decisions, right? Some of those tasks may have some type of deadline. You have to respond to this FPGA in a certain amount of milliseconds, blah, 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 blah. So you correctly identify, hey, the real-time kernel is probably a good fit here. And so you go out and you start collecting reference boards. These reference boards, like maybe a few of them will fulfill all your requirements, right? And do so in a timely manner so that your system will perform as you expected. But I work for an SoC manufacturer. So wouldn't it be great if that SoC that fit your requirements was a TI SoC? So it's in my best interest to make sure that our reference boards and everything that we do performs in the absolute best way we can, right? Especially for the your real-time Linux application. So, okay, quick refresher. Real-time Linux, the whole idea is to maximize the time the CPU can stay in a preemptible state, right? We want to be able to interrupt it whenever we want to. This allows the scheduler to recalculate what needs to be running on a CPU as often as it wants to. Oops. And it allows the most important task on that system wanting a CPU to run on that CPU. In other words, as Stephen likes to say, it's a deterministic operating system. It is not mathematically proven, but through testing, we can be sure that the system will behave exactly as we want to. But all this work is essentially trying to bound latency. We don't necessarily have any guarantees on how fast we can respond to it. Even the real-time kernel will actually increase latencies in certain situations. But at least they're bounded. However, that's not what people do, right? They get their hardware, they get their reference boards, they start running some evaluations, some tests, and they order it, right? They say the latency graph on the right is worse than the latency graph on the left. It doesn't really matter what the hardware is. It's left is better, right is worse. So how do we start tuning that system so that we can, or tuning and testing that system so that we can get the fastest latency responses in the real-time kernel? Once you start going down this path, the first thing that you're going to do is start experimenting and testing. That is inevitably going to find bugs in your software. It's just a fact. One of the first things that we ran into is we started making optimizations, started experimenting, and we started getting this blip. And we had no idea what that was. And it was like, oh, that's not good. So through a little bit of tracing and a lot of banging our heads against our desks, one of our colleagues was able to figure out that it was an RNG driver in Opti. So in the trust world, we would go, the kernel would ask for a random number. We would go and switch into the secure world context. Secure world context would ask the RNG driver, like, hey, I need a random number, and the RNG driver would sit there and spin until we would get a random number back. It was 1 in a million chance. Quite literally, it would happen 1 in every million times. The last slide, it was little, but through enough testing and the length of testing, you're going to find it. Which just means
it told us that we have to test the entire system. We can't just sit there on the kernel and QEMU and just like, oh, this is going to work, this is going to work. We have to go from bootloaders, firmwares, kernels, everything. So how are we going to do this, right? Right now everything is manual, so how do we automate this a little bit? If you look at our architecture of how interrupts can get to the CPUs, it can get overwhelming really, really quickly. So what options do we have? The first thing is just start off easy, right? StressNG, Hackbench, these are well-established tools that do a lot of things that can generate a lot of noise, interrupts, anything that you want to do in certain situations. We can then use RTLA, cyclic test, whatever we want to test the context switch latencies with those things running in the background. We can, in this example, we're using CPU method all. It's just creating a busy loop. We're calculating Fibonacci or whatever. And then we have a real-time thread that wants to interject. And so this is essentially just testing how good is our timer interrupts working. Are they working at all? We can then start swapping out different background loads. For example, this one, perf, is adding Ethernet background loads. Can we pump a gigabit through our Ethernet switch and still context switch in a reasonable amount of time? And then another one, because we're SoCs, right? We have GPIO. We love GPIO. This one is a little bit harder. So we can take a single pin, connect a wave generator or a signal generator to it, and then have some user space application try to mirror that state. And then we can put a probe on that second line and then use a persistence capture just to grab the minimum latency and then the maximum latency as those waveforms are triggered. And so that's basically the whole idea, right? So we just start piling on more and more tests. But so through all this experimentation, what did we figure out? We quickly learned that everything is a balance, right? We prioritize the GPIO IRQ. That's going to kill our Ethernet IRQ. We start increasing the timer interrupts. That's going to add more interrupts, which is, they're not as transparent as they should be. Or, well, they are as transparent as they can be, but that's still a lot of interrupts that takes time away from the real-time threads. So we're kind of bounded ourselves, right? We have hardware. I have hardware that I want to sell to you. So it has, instructions per second. It has everything we do, and we can't prioritize. So what are we ending up with? The only thing we can really do is start eliminating unnecessary things. One example is just remove unnecessary services. You don't need a display if your system is headless. You don't need a GPU stack if all you're going to do is take Ethernet in and toggle a GPIO. So a lot of work went into ensuring that these interrupts are minimized, but they're not transparent. So we have to eliminate things. One of the biggest things that we actually figured out through all this is the kernel size. We have A53s. Those are our lightest CPUs. They're in order, dual stage, 8-issue pipelines. So we're kind of stuck. The instructions per second is really one of those things that we have trouble with. So we just started eliminating everything that we didn't need. There's hundreds and hundreds of lines of just removing everything that's built into the kernel. This really saved a lot of our page faults. This did a lot. This did a lot. And sorry, I'm losing my train of thought. So this did a lot to help our systems behave properly and decrease the latency. But it gave us another problem, right? So we have all these configs that improve the TI SoCs, but I mean, we just ripped out QNX and NXP and everyone else. So what are distros going to do? And that's one of the things that I didn't answer here. And one of the questions I was bringing up yesterday was, we don't have an answer for this, but it is one of the things that we wanted to take care of. We did figure out that, yeah, we can take about 2/3 of our latency away by reducing the kernel size. ARN's been experimenting with 32-bit kernels as these SoCs get smaller and smaller. But like I said, it is every SoC vendor will have a different config, and these distributions are going to need to find a way to support all of them if we need to. And that is basically everything. That was very fast. Does anyone have any questions? I hope we have 20 minutes of questions. My hope was we could start a conversation about this, but it's a little late. No? Okay. Well, all right. Well, you can contact Pekka and I anywhere. Email, we monitor email always, obviously. We're also on LibreChat. I monitor IRC pretty regularly. If any of you guys have any questions, please feel, oh, sorry, not looking. Yeah.
Thanks for the talk. I guess what you guys are doing is basically the best you can do. For your users, it's going to be up to them to optimize their system, shrink down the configuration, and optimize their stack, prioritize everything that is important and everything that is not important. But what you are doing, like benchmarking regularly the system, making sure that opt is not going to get in the way, that your drivers behave correctly, is, I think, the most important part in that. So that was my remark. So
yeah,
thank you.
No, yeah, that was one of the things that was interesting. Is everyone has drivers. We have the evil vendor tree. You know, everyone wants the cutting edge, but being able to test that and standardizing the test. Like right now, it's everyone kind of does their own thing. There's really no like these are the tools that you need to run to test your system. Everyone has a different config. Everyone has a different way to test it, and so nothing's really standardized is what we found. Behind you, sorry.
So first question, have you actually analyzed how these latencies have changed over kernel releases?
So that is one of the things, so this has only been about a little under a year. One of the things is as we move kernels, it is getting much, much better. But it is getting much better, but it is harder to check every single driver. So like, for example, our GPIO driver actually has 2 IRQs fire. One for the GPIO bank and another one for the actual pin. And so it quickly becomes a problem of scale. You know, most of these tests take about a couple, 6 hours to run just to make sure that you get a good snapshot. But you have multiple kernel versions, multiple UBOOP versions, multiple OPTI versions, multiple TFA versions. And so it's one of those things like, how do we scale up? So, yeah.
Okay. And yes, I agree that Tux is getting one fat penguin recently.
Yeah.
I can remember times when you could build a kernel in about a megabyte, and now you're lucky if you get something that is about 30.
Yeah, that was something I wanted to talk to Daniel and Sebastian and Thomas yesterday about. Is it's almost, it feels like I need to go through kconfig and just make sure everything matches up. I don't. That just seems like pain, and I don't want to do that. But I can't think of a better option.
Yeah, so I was also recently playing with one of your hardware regarding RTE. I managed to get horrible numbers. I didn't have the time to look into all the details. At least I tried to address some of the findings you had and then try to evaluate them. So one of the findings definitely is that you need to be very clear in how you run all these workloads and tests, ideally in a reproducible way, just to avoid that one-off mistake that everyone is making possibly while trying to replicate it from slides to code or to shell commands. So that would be valuable to have that. And the other thing, obviously, is, as you mentioned, there's so many versions of pieces and bits that you can integrate, possibly in the accidentally wrong way. So having the reference image there as well. So my question would be, if I have, now I know, I have a Beagle Play at home, what should I build to actually replicate the numbers you were running so that I can then prove if I can ruin them again, or if I just made in my own integration a mistake, and yeah, that should be then sorted out. Just to give an additional data on that, so you may know I'm maintaining the Xenomai project. We have a similar problem there as well. We haven't solved it either, but at least we have some aspects of this. So we are providing reference images, so build system to generate them. We are using them in our CI. This is also covering the one of the millions of possible paths. At least we can point people then, if they come back with, my latencies are off, to the reference config or the reference build and say, okay, can you reproduce it there as well? And we may have a bug. If you can't, then we may have a problem in documenting certain of these optimized switches. We have Intel there as well, who does something that they have their own variations, but I can also pull them in and say, okay, look, do we doing something weird there in our reference configuration, or do you have a better one? Or is it really something which is a problem that should be addressed in one way or the other? So this helps tremendously to avoid this, everyone does some measurement, no one understands the result, but everyone is talking about a problem that we have for decades in this area. So many measurements, but nobody really understands really the details and the problems around that.
Yeah, that is 100% the big gap, right? You have core real-time people that know this system in and out, but once you start dealing with use cases, Ubuntu has their own configs, Debian has their own configs, we have our own configs. Which ones matter is something we haven't figured out yet. A lot of these tests I wanted to start automating and putting into LPT or something so like kernel CI could run. I mean, it's initial stages, we're talking about it, but coming up with some type of baseline that we can all measure and commonality is basically what we need.
Kernel CI has now the RT tests running, and the data is being collected, it's not being completely evaluated, but Daniel Wagner just recently pushed that forward. But this is one step as well, because then you can throw also variation of configs of things on various boards. But yeah, again, the point would be if someone comes around with a number like which is bad, how to validate the
exactly,
mistake. Yeah.
Exactly. OSADL is doing the same thing, just working with them as well, yeah.
I'm curious if you guys have, since Pekka, I know you're working with Pekka, but we're talking about cyclic test and the kernel. Have you guys looked at also measuring, many of the new use cases involve, network, often real-time network of some time, and looking, adding that into your system of, that's kind of another thing on the problem of, because the real-time has to go, okay, the compute side and the network side. I'm just kind of curious if you guys have any thought on that, right?
So we do. So a lot of this came from a customer running EtherCAT. They had some type of minimum latency that they could experience, and we really wanted to push to make that better. So we do have a lot of that. It's still very, very manual. So we set up a small little GPIO bank, and then just did we make that packet frame, and that's basically all we're doing right now.
So you had the picture of the minimum and maximum latency. I was wondering if you had some numbers for what you were able to achieve when you optimized for GPIO.
So that is one of our weaker ones. Because we have those, you can always increase the IRQ priority. So you can, once you move that to the top of the stack, everything else goes down. But I can't quote myself because I don't remember, but it was reasonable for what someone wanted to do. Essentially, we had someone who had an FPGA that wanted, I think it was like 500 microseconds. It would toggle a GPIO. We would go do a DMA type transfer. So we just wanted to make sure we were under that.
Okay, so on the order of like hundreds of microseconds.
Mm-hmm.
I think another related question would be, could you tweak things to minimize the deviation, like the difference between min and max?
So that was one of the limitations that I put on us. We can isolate CPUs, we can do all those kind of tricks, but for a general use case, we didn't want to say like, hey, you can only use 3 cores and one of them can be a real-time core. Because other people will have multiple real-time tasks or no real-time tasks. And so a lot of what we did was we're not going to do that. We did play with like the tick timer. We increased the tick timer and then we went to like a no hertz type thing. So if you have a single real-time thread, that CPU's tick will be turned off to kind of give the CPU more time, or the real-time task more time on that CPU without being interrupted constantly. But yeah, that's about it.
So yeah, I think I was going to add a couple of comments of we did something similar to what you've been doing back for a customer in 2018 and published some of the results, and I think that shows whether it was not on an actual ARM system, it was one of those other manufacturers of very similar problems of the kernel configuration, removing any external influences from other parts of the firmware, and pretty much that still holds today, although I think what we're seeing from the distribution point of view is the real-time configurations are a lot better. So you can do some pretty good stuff on a laptop and get microsecond responses, as long as you don't mind not having anything else going on.
Exactly. So that's, if your tolerances are big, you have a microsecond, it'll work out of the box. But once you start like saying, I want under 100 microseconds, you start running into problems where you do have to tune the system. And so, again, one of the things we kind of talked about yesterday was documentation. Like, there's lots of levers, which ones do what, and how to do that is missing right now.
Yeah, I found a very interesting little corner case in StressNG.
Yeah.
Which I've just had it actually been fixed. If you run StressNG and its first thread gets emitted into, say, shed deadline, but then further threads don't, it doesn't notice.
Yeah, yeah.
And you sit with some well-behaved RT threads and some very unwell-behaved non-real-time threads that are then trying to eat the rest of your CPU.
Mm-hmm. Yeah, there's always those little corner cases, and I purposely left out a lot of the debugging that we did, mostly because every single time it was different. The opti bug, it just happened to be a passing conversation with like, oh, hey, we enabled this feature, and I was like, oh, that's probably what broke it.
We've seen very similar with things, even perf will cause you problems because it has to, at occasions, do its own maintenance on the buffers, and you will see it in its own tracing invoke itself to flush the buffers out, and you go, well, thanks, I now missed that period.
Yeah, exactly.
There were several talks at ELC with regard to the K3 and how complex it is with lots of firmwares. You have the DM firmware, TFA, and you talked about a bug that you encountered with Opti. So at some point, the kernel can be as real-time as you want. The problem will be there from the accessing these firmwares. Do you have some kind of automated testing or effort to make sure that these firmwares behave as you expect them to with regard to real-time use case in Linux?
So right now, nothing is as automated as I want it to be. So we do have like a CI and a continuous integration build system, but it is one shot, yeah, right? So we have this potential candidate, we're going to build everything, and then we'll run tests. Those tests are very much pass-fail, and so there's not a whole lot of gray area, like, hey, this is better or this is worse, kind of flags that we can generate. So right now, it is definitely just a manual slog of like, okay, here's a snapshot, what changed? Yeah, unfortunately. All right, well, thank you guys. I will.
There's also this other problem. They have their own methodology, which we get with the customer. Say, okay, OSADL says this, I have this in house, and yours says this.
Exactly.
So it's like, you know.
That's another problem we have, is OSADL will add tracers. That was one of the first things we agreed on. Just get rid of it. And so
what's the purpose? Do you want to qualify if the system is crashing?
Yeah, exactly.
Or not crashing, or do you want to get the best numbers out? What can the system do? You can't do both at the same time.
Exactly.
Well, the same purpose we use that is we want to know what was interrupted. And sometimes it's like the timer, the perf itself, storage device.
And then you want to look into the quality, not the quantity of the version. What is the structure you see? Well, there you can turn on tracing, but then the numbers should be ignored. There should be a big sign reading. Don't look at the numbers, look at the trace of events coming, the code files.
Even Daniel's RTLA, I mean, he opens up a very small amount of tracers, but we still see it on our.
Yeah, sure, that's the point.
So
but regarding the question was from you regarding how to do the automatic evaluation. Daniel Wagner has some ideas for quite a while. He was working on that.
Oh, okay.
In kernel CI context. So the point is the numbers are there, the data are there, but you need to visualize the trends.
Yeah.
The individual number is useless. On an individual board, individual configuration, it takes someone to look at it. No one knows. So you need to have some kind of trace visualization that people who are maintaining real time and evaluating have some kind of quick shot, or even at some point, the automatic information you're drifting away. That is something we discuss it from time to time. Again, if you have ideas or desires, get in contact with them.
Okay, yeah, definitely. Cool. Well, thank you. I didn't know that. Right now, all we have is like a boot test. And so
you have to sit with them in the same car, drive them to the same event. No, not only, but it's actually happened to me. Some exchange on that.
Oh, cool.
And I recently picked them again on this, and then came the patches for kernel CI regarding test enablement, which is just the first step on that.
Yeah. Good. That was one of the things, like, we can throw it in our internal build system. Like, what's the point?
Yes.
Yeah.
You even have this functional testing. You are looking at, because there are so many false positives or uninterested results that no one sees that one off.
Did I introduce you to Nishant or Barry? He's the one that runs our test farm. I don't think I did. No.
something we had a discussion with them on. I mean, I think we need to help them. I mean, you know, they're doing stuff, and I think we can work together to make them what they do really well.
Yeah.
I think they do a great service, but
No, they
you know,
really
they kind of we found it like, look, they're doing this stuff, but you know, every I don't know 6 months it comes up because some customer, yeah, I saw this Osado, it doesn't match what you guys are doing, you know, and I don't have this, right? So and I said, well, don't blame Osado. Let's help them. It's the same problem we talked about this whole thing. Is look, there's a million ways to measure these things, a million assumptions, and a million things in the system config, and you have to pick one.
Yeah, exactly. Exactly. Hey, how's it going?
Although I was late to your talk.
Oh no, it's all good.
But actually, I had to talk about the octopus thing.
Yeah. Yeah.
I'm curious to know what kind of bug you found with the RT thing.
Oh, okay, yeah. So essentially what was happening is we have a random number, a hardware-based random number generator. We wanted to demo how you can flip-flop back from the secure world to the unsecure world. And so we gave the RNG hardware device to Opti. But the kernel still needs RNG, right, for like stack randomization and all that stuff. And so it would periodically go into Opti to get a random number and come back with that random number. But what was happening was if Opti didn't have the RNG, we would go into a spin lock and just wait for Opti or wait for the hardware device to generate a new number for us. Spin locks in Opti disable preemption. We didn't know this, and so 1 in 100 million chance we would sit there and stall the CPU.
Was that the actual number? 1 in 100 million?
So we ran a 6-hour test with it was about 100 million samples, and about 100 of them would.
Actually, that Linux driver was something that I contributed.
Oh, really?
So the Opti-based RNG.
Yeah.
That had requirements. That
Mhm.
You can't give the random number directly with non-secure because there is requirement from Opti to use random numbers.
Yeah, and so that was one of the things was.
This is a real thing. If you might have seen patches from SD.
Okay.
Opti, they are about to reduce the number of spin locks.
Oh, good.
Within Opti.
Yeah.
So yeah, you shouldn't use spin locks, but rather use mutexes.
Yeah, we had no idea. So in the kernel, spin locks are basically, you know, are sleepable. You can sleep in a spin lock, but you can't do that in Opti.
With RT enabled, you can sleep in spin locks.
Yeah.
Not on the main line.
Yeah, exactly. Exactly.
So, yeah, but in Opti, that's the usual convention. Actually, the usual convention of a spin lock is like block the CPU.
Yeah, yeah.
In the kernel, they have converted to raw spin lock and the spin lock API
Mhm.
because they don't want to change the timers and all the systems
Yeah.
using the spin lock API. So that's why they change it to raw spin lock and the spin lock API.
Exactly.
So that's why. And in Opti, spin lock means you have to lock without receiving any interrupts.
Mhm.
And that's the real thing. And we're looking into Opti and trying to minimize all those spin locks.
Good.
For patches at the end of the
Okay.
So we have concentrated a lot.
Good, good, good.
Yeah, but yeah, Opti is going to add.
Yeah, yeah, yeah. Yeah, yeah, yeah. Yeah, yeah, yeah. Okay. Yeah, that was another thing. I basically limited myself all the way down to just like the only thing we can do is just reduce kernel size.
Yeah, basically I think we are focused on like what the existing latency is.
Yeah.
Without system being able to see.
Yeah.
So
platform trusted execution environment. So in the ARM world, you have like certain registers that are protected, and you can only access them in a certain mode. So Linux you can switch the CPU into the secure context and run in the secure mode, and then switch back. So you can switch back and forth into like a secure mode and an unsecure mode. So no, it's CPU based. So it's a register. And so you have multiple exception levels in ARM, like EL 0, 1, 2, and 3. 3 is basically that hypervisor mode where you can go into 3, go into your trustful zone, and now you have like a secure world 1 and secure world 0.
There are lots of Russian dolls there.
Yeah, exactly.
There are lots of talks online to search for Opti project. You can see the introductory parts. Yeah, there are lots. And about trust zone, you have heard about trust zone as well. Yeah, there are lots. So yeah, actually the mutex thing conversion would help me a lot.
Yeah.
Because mutex, how it's implemented in Opti, that we allow the cores to wait in the normal, so that we allow them to handle the interrupts as much as they can.
Yeah.
Rather than waiting in Opti, we want cores to do any of the stuff that is available in Linux kernel normal applications.
Okay.
That's the design
Super. I'm so sorry. You boot, right?
I work on different things.
Yeah. But you were doing the upstream stuff.
Yeah, the device tree stuff. Yeah, that's something that I got just involved in.
Okay.
Because of my reviews role in U-Boot for Qualcomm platforms. I was like, when I was reviewing those supported device trees,
Yeah.
I was like, can we have a solution and that led me to that sort of thing.
Okay.
And yeah, my team at the now was very supportive. Yeah, go ahead.
Yeah.
Support something.
Yeah, that really helps, especially like TI, where we have to like manually sync, and we have so many SOCs now that it's just that was becoming a burden. Yeah, that just really streamlines it.
Yeah, definitely. I think it's useful for you guys and others as well, especially from Qualcomm side. We see that usually we only have to add drivers, we not give notification.
Exactly.
We try to use mostly upstream DB on Qualcomm, so that there are some fixes we are still good in that, but yeah.
Yeah, we do the same thing.
But again, we want those details to go away.
Yeah.
And I'm always like, whenever someone sends a patch in the good details thing, like, can we do it somewhat better? Can we reduce it? Because that helps you. You don't have to care about it. If you do that and get rid of those customization layers of the machine, you are free from the device. Only the testing, if you run your CI pipeline, whenever the next thing happens, and you get to know whether the upstream is working or not.
Yeah.
And you could also think at your end as well.
Yeah.
And do the CI testing so that you are ahead of your driver development and you think that needs fixed.
Yep.
Yeah, so I hope it works out.
Me too. Yeah. I mean, this is kind of the beginning for us, and so we'll see what next year holds. But it's gonna be good.
Yeah. So I'm mostly involved in platform security. That's why I was interested in learning from the technology.
Yeah.
And because we work across the years, bootloader.
How hard is it actually to compare two K-config snapshots?
Well, so the problem is No. So like one config option will do a limited amount of work, but what happens is okay, so you use like a tickless kernel, right? So you don't want a tick happening when there's only one task in the scheduler, but you can also offload your RCU callbacks, and so all of those kind of magnify each other, and so all the different combinations that you can do just turn.
You have all these independent variables.
Yep.
So you just can't
So print K is the last remaining thing. So essentially, like, you can't preempt.
The print, it's everywhere in the kernel?
Well, no. So if you, yeah, the only real. It's okay. So the really what's happening is when you're printing to a line to the console, that CPU printing can't be preempted, right? Because it has to finish that line. So the original solution was just don't allow that. You can't print to the console. But Linus saw that and was like, no, that we can't just disable options and say you can't do that. So it turned into like a buffer, like a ring buffer. So if you want to print something, you put it on this print buffer, and then when the CPU has time, like there's not a high priority task running, it can go and start printing everything to the console. But that way, it's always preemptible. Yeah, it's because it's messing with the TTY layer. It's just pain, and I do not envy Sebastian or Thomas doing all this work. I'm glad they're doing it. But they are the real-time Linux maintainers. All right, I'm gonna go get something to eat. Yeah, it was great meeting you guys.
Surendettement. Voilà, en fait, peut-être comme un connard. Création ou reprise d'entreprise, installation obligatoire de création de salariés, gestion de société. Et je te jure qu'il y avait
Oh, it's like for my no, my laptop's resolution is actually higher. What should I set it to? 19. Yes. I think it's got the defaults from HDMI. Should I set it to primary? I think it's better now.
No dongles, it's straight HDMI in. Think that. But yeah, if you could bring a dongle, that'd be helpful. Thank you. And you just change it to primary?
Yes.
Yeah. Does that make sense to you that that would fix it? No. Yes. Are you gonna bring down a USB-C switch?
Sure.
In the meantime, I can help you out.
Yes.
And would you take your badge off? Yes. Adjust that. This will go right here. Perfect. And then there's just an on-off switch whenever you're ready.
Should I test it now?
You can.
Check, check. It's awesome.
Test.
Success.
Viewed by.
Test, test. Okay, it's time. Hello, welcome to the BOF. My name is Bartosz Golaszewski. I've been working with open source for 15 years professionally, and I've been an amateur even before that. I maintain the GPIO subsystem in the kernel. I maintain a couple drivers and some user space project. I've contributed to many different things. These days I mostly do kernel, but over the time I've done build systems, user space, and whatnot. And I'm quite passionate about coding. I like software development. I am based in France, as you can tell by my typically French name. And I work currently for Linaro. You can tell it from this angle. And I'm in the Qualcomm landing team. So yeah, that's it about me, and thank you to Linaro for having me here and getting me to work on interesting subjects. Check us out, we make software run on ARM. And with that out of the way, if you have 5 hours and want to catch up on the issue, then this is a good starting point. So make sure to download the videos and watch them on your return flight home. The problem statement. So, oh yeah, and this is a BOF, so don't be shy. Please take the mic from Fabien, and if you want to, get on stage with me and talk some more, that's possible as well. Do you want to start changing? I don't think it's necessary. So, yeah. So, okay. Problem statement. So, drivers. Resource provider drivers in the kernel do often 2 things in probe. They will allocate some memory in probe that will be freed in remove, and they will register themselves with the provider subsystem, which can be visualized like this. And what is the problem? The problem is that they allocate often struct device, which is reference counted, but they free the memory where it's stored in remove. But there can be still references held to that struct device. And some subsystems just crash, others have some workarounds, some get it right, most don't. And the solution is actually quite straightforward. Struct device must survive driver unbind. Or rather, the subsystem must be able to handle the provider data disappearing suddenly, because the drivers can simply be unbound at any moment, especially if they are on dynamic buses, even indirectly, because you can have a driver that is never meant to, or theoretically never meant to be unloaded, but it's on a dynamic bus a couple layers below, like an I2C adapter on a USB device. Why do we allocate those struct device instances? Basically what we do, we often have this split between physical device representation and logical device representation. So in this case, we have a platform device or whatever device that will come up when the device is detected and probed, and it will create a logical device, so not a platform device, but for instance, an I2C device or a GPIO device that will be underneath one layer below, and this is what I refer to as a logical device, where you can have 2 devices representing 2 GPIO banks on a single chip, which one layer above is represented as a single platform device. I've noticed that this is a major issue in the kernel. Well, I wasn't the first person to notice it, but I started working on that. And the first thing I wanted to fix was the GPIO subsystem, because it suffered from from simply crashing whenever such a situation would appear, that you would have a GPIO chip that is being used by someone, and then the provider of that chip disappears. The user tries to use it, dangling pointers, bam. I think that there are several ways you can fix it, and I like one especially, so I used it to address the issue in GPIO, and I'm happy to announce that in 6.9 this will no longer be a problem of the GPIO subsystem. The code has landed, and right now the GPIO chips can handle, or rather the GPIO subsystem can handle GPIO chips disappearing. I will first present the approach I used. I will present another one that seems to be popular among the people that fix subsystems that exhibit that problem. I will talk another, I will discuss another third way of doing it. Then I will hopefully get some feedback on it, and maybe possibly even more approaches. And finally, if time permits, I want to discuss device links. So I call my preferred solution the split responsibility, where what you do is you have your subsystem that defines the implementation structure for the provider drivers. And what you have in that implementation structure, you have some data. You can have your name, you can have some callbacks that the subsystem will use to call into the driver, some additional data, whatever. This is a very simple example with a simple callback and a name. What do? The provider drivers starts probing. It allocates this structure. It may be part of a bigger driver structure if needed, but in this case, it allocates the structure. And then it registers with the subsystem. As you can tell, there is no struct device yet. It was not part of this implementation structure, because what happens is that it's the subsystem that allocates struct device, and it's a private structure that the provider driver has no access to. So in GPIO parlance, this would be the split into struct GPIO chip and struct GPIO device. GPIO chip is something the driver allocates. GPIO device embeds struct device and is something that the subsystem allocates. The difference is that the former is, its lifetime is tied to the driver being bound to its device. For the latter, it's reference counted because it embeds struct device and it uses struct device's kref to count references. So what the subsystem does is it has the device structure, which embeds, as I said, struct device, and also holds a pointer to the implementation. And the pointer, as you can see, is protected with RCU. Why? About that in a minute. So when you, from your provider driver, call into the subsystem, you go into the registration function, and what it does is it allocates memory for the device, initializes the internal device, and that's it. It will never free it. It will assign it a release callback using the device type structure. Why RCU? Because with using SRCUs, not RCU, because we may want to sleep, so in this case I settled for SRCU. You can, whenever you go into the subsystem and you call a whatever API, you simply enter an SRCU read lock section. You dereference your implementation structure using the provided API, and then you can call your function, your driver implementation, while still being in the read lock, SRCU read critical section. And then whenever your provider driver is being unregistered, what you do, you set the implementation pointer to null, and then you synchronize all SRCU critical sections. This is what GPIO does right now. Every API function is inside the SRCU critical section. They all can run in parallel, and they will get synchronized once the provider driver is removed, so that we don't really null the pointer until the last critical section ended. Then we synchronize, and then whenever a new API call comes in, it will see the pointer, the implementation pointer being null. It will run a check and then say, okay, no device, bam, I return an error. Does it make sense? So this is one approach. Another approach, and this seems to be used, like I saw some patches for the PWM subsystem that use that, is a bit different. It tasks the provider driver with allocating memory for struct device, but instead it asks the provider driver to hand over any memory to the subsystem, not free it in remove. I don't like this approach. I will say why. But first, how does it look like? So it looks like this. The subsystem gives us, again, a definition for a structure. Some callback in that structure, right? We can put them in a separate ops structure. We have the name, we have the struct device embedded in that structure, and the callbacks. What does the provider driver do? It allocates the memory, but not with a generic kmalloc. Instead, it uses an interface provided by the subsystem. So in this case, the subsystem gives us bar alloc data. It's not a devm interface. It's pure, and there you will not see any. Well, you have the bar free data, but it should not be used other than in error paths in probe. Instead, what you do, once you register your data with the subsystem, it's considered owned by the subsystem. The driver no longer controls it. So when the remove is called, the driver will not remove it. Instead, it will allow the subsystem to release it. Why don't I like it? So the argument for using that is because you only allocate once and not twice. Memory is so cheap, and this is not a hot path. This is a driver probe. It doesn't matter really. Instead, what you get is something that is looks confusing, because there is, in software, in coding in general, if you allocate something, you have to pair it with a free. If you allocate something and then hand over the ownership of that, it looks sketchy. Something's not right. Your internal static analyzer. Yeah, Fabian, can you give the mic to Krzysztof? Your static analyzer in the brain will complain.
It feeds trust. You pass the ownership.
Yeah. Does it though?
Can you tell which subsystems use this model?
So I recently saw patches for that for PWM, and there are, I think, I'm not sure if SPI uses that. There are several. I would need to check again, but this is something that you often see, like full alloc data, and the drivers will allocate that data using a provided interface instead of allocating it themselves. So it's definitely, I think this is more common than what I presented, actually. What I presented used to, so what the first solution used to be used by GPIO before, but it was wrong, and it would crash. It's still wrong, for instance, in regulators. In certain instances, it can still crash, because there's no synchronization, like what I introduced with SRCU. So, yeah, so these are the two main approaches. And then there's something that I call read-only config structure. This is something that, for instance, NVMem uses, where you don't task the provider driver with holding any data. Instead, what it does in probe is it allocates some memory on the stack, which holds a config structure, and everything in that config structure will be deep copied by the subsystem. So what the subsystem does is it takes the pointer during bar register, it copies all the data it needs, and then after the function returns, that memory is irrelevant. It can go away. So if you register an NVMem device, you can have your NVMem config, or if you're registering a regmap, for instance, your config only needs to live for as long as the registration is happening. Once it's done, you can dispose of it. So this is probably even a better approach, except that for GPIO it wasn't possible because we have so many drivers that would need to be converted that it doesn't make any sense. It's better to allow them to have the implementation structure embedded. So why am I talking about it? Because there is a lot of talk recently about making sure that we can put all kinds of devices that were not previously meant to be hot unpluggable on devices that can in fact be unplugged at runtime. And while yesterday we had a discussion about about the impact of that on device tree, on OF implementation in the kernel, I'm arguing that without addressing the subsystems that cannot handle hot unplugs, we will not get it to work anyway. So this is why I wanted to discuss this one. So these are the three approaches that I've seen so far. The first one that I use personally. Are there any more? Are there any opinions on the three? Are there any new ideas? What would you do to make sure that your non-dynamic devices can actually be put on dynamic buses? Awesome. Another thing that we have, if you talk, for instance, to Saravana Kannan, he will tell you that all this is irrelevant because this should all be handled even before we probe with device links. So if you are familiar with device links, this is the whole mechanism that will allow us to enforce a probe order whenever you have resources that are requested by consumers. These consumers should never be probed before these resources are actually available in the provider drivers. And in theory, this is awesome, but it doesn't really work all the time. For instance, I have posted an example on the mailing list of using interrupts with GPIO interrupt controllers, where despite having device links set up, they will not work, they will not be enforced because in the interrupt subsystem isn't really integrated well with the driver model. So when you have an interrupt controller getting probed, it's not aware that it's tied to a certain GPIO device, and it's actually very easy to with a device tree based system to generate a situation where you will have a whole lot of stack traces from the interrupt subsystem if you unbind the GPIO controller, which is also an interrupt controller with interrupts requested by some users. If you unbind that GPIO controller, if you request the GPIOs, then the device links will enforce the unbind of the users of those GPIOs. But if you request interrupts from that GPIO controller, this is in turn orthogonal, so the actual GPIO controller doesn't even know about those interrupts being requested, so device links will not work. You will unbind the GPIO controller, bam, the interrupts will still be requested, they will still dangle. It doesn't cause a crash because of how interrupts are numbered, but it causes a bunch of stack traces it leaks memory in procfs and sysfs and does a bunch of other problems. So I tried to address it, and I got yelled at by Thomas Gleixner, and then somewhat figured out that I will leave it for now, but probably should be revisited at some point. So yeah, so this is what I prepared to start the discussion. So now we can discuss. Yeah, go on.
So my understanding of the topic is a bit limited, but one overall question is, in many cases, the relationship between various devices, like the GPIO, which provides an interrupt, and the interrupt is used by some peripheral. It is probed from the center, from the CPU to the periphery. And then if, from the point of view of unloading, you unload from the periphery to the center. So in the practice, while the problem exists, I think in many realistic cases, it won't happen if you consider loading and unloading of drivers, of overlays, for example. So the question is, it happens, it is easy to reproduce this sort of problem if you manually unbind the driver, but does it even make sense to unbind the driver which is used?
You can very easily reproduce it if you have like a GPIO. During our discussion yesterday, I mentioned the CP2112, the HID expander with an I2C and GPIO chips on board. If you plug it in, you get some devices. You can create those devices from user space over sysfs. You can request those GPIOs from user space. If you plug it, if you unplug it, you'll trigger those crashes. Like not anymore with GPIO. With I2C, you will actually freeze one of the kernel threads that does the remove. If you try to unplug it with users still active, and you don't need to. If you're limiting yourself to only devices probed from device 3, yes, device links will probably save you. But if you have anything else that is not covered by device links, then you will easily trigger the problem. Not only with like strictly theoretical unbind over sysfs. Like this is something that can happen. This is how I noticed it. So just by doing a manual unplug of a used device. So this is definitely something that that happens, and there's Brian in the back. If you could pass the mic, please.
So I was just wondering, Bart, your preferred solution, though, does it actually address the problem where you've hooked an interrupt on a GPIO, and then you would pull that USB device out? Does it not? Does the device link?
No.
It's the same problem, right?
It's the same problem. It doesn't cover it because the problem is in the interrupt subsystem and not in GPIO. The problem here is that what happens is you register an interrupt, an IRC chip from the GPIO driver, and whenever this interrupt is requested with request IRC, so Thomas Gleichner argues that users should have a way to be notified about the need to release or to free all interrupts. I'm arguing that it is not possible. Like, how would you do that? Like, device links are there to address that, but it doesn't work because the interrupt subsystem is not part of the driver model. So the device links in this case are wonky at best.
Two problems that you solve.
Yeah.
The first problem, which is pulling it out for the simple GPIO case, and then the second problem.
For interrupts, which is still an issue, yes. Yeah, so this is still something that needs addressing. Can you pass the mic to Krzysztof, please?
Yeah,
Yeah, you asked for one more solution. So I think the NFC subsystem uses something like this regular buggy choice and just puts everywhere test bit, whether the adapter was removed, adapter was unplugged, like things like that. So all such callbacks, which some provider in this framework calls something, always checks whether everything is running to avoid it. So.
But is it within some critical section? Is it locked? Because if you check the bit and then proceed, then
no, NFC is broken. I mean, it's spaghetti code with thousands of bugs, and Syscaller brings every month several new bugs, mostly because someone added a virtual NFC device. So NFC is the near field, so a network device. So someone brought a virtual device, so you can test the NFC code on a virtual machine. So Syscaller now is testing, and it's like sincere, it's bringing issues. So, but the idea was that they solved the solution with test bit or test flag, which of course is obviously wrong.
It's not totally wrong. It can be a solution, and you don't even need a special test flag. What you can do is use the existing flags in struct device. Like struct device has the K objects in, I don't remember what it's called, but if you call device is registered, it will check a specific bit. The only thing that's left is just lock that state. So use, I don't know, read-write semaphore. And
yes, but if device is being removed, the struct def is also being torn apart.
No, you take a reference to it. Like if you're using it, then you should have taken a reference to it. So the solution is not entirely broken. I do that, so I posted patches recently for a new subsystem. It's called power sequencing subsystem. And what I do for those power sequencing devices is I register them. I use read-write semaphore, and on every API call, I take the read log. I check if that device is still registered, the provider. I do my stuff still under the read log, and then in the remove I take the write log, I unregister the device, I release the write log so that you cannot have read sections at the same time doing anything. When they will, eventually be let in, they will see that the device has been unregistered and they will return. So it's I think it's a slightly easier than the SRCU solution. But for GPIO, why did we use SRCU? Because GPIOs are complex and, well, how hard can it be, right? You can toggle GPIOs or read GPIOs from atomic context or from process context, and the drivers on the other side can sleep or may never sleep, because these may be MMIO or I2C drivers, and you never know. So you have, atomic context, process context, sleeping drivers, non-sleeping drivers, and neither spin locks nor semaphores or mutexes will work. So the only thing left is SRCU, which allows you to be called, like enter the read section from any context, and also call whatever functions, sleeping or non-sleeping functions from those read sections. Like, I would have used a read-write semaphore, but it was not possible because of those complexities. So yeah, to summarize, checking a bit is not wrong, but you need to account for the state changing. Like, if you just check the bit and go on and assume that it will not change, yeah. So I would, if I were to recommend something for the NFCs, just use some kind of a fast lock and read-write semaphore.
Did you get any feedback from other people on the mailing list for your SRCU solution? Like, I don't know.
I got feedback from Paul McKenney, the author of SRCU, but he just he reviewed the patches, so he said that he doesn't know if the approach is right, but the code looks right. So technically, it was done right, but whether that's the best solution, like I think I've asked that question several times. Like, does anyone have any better solution? Never heard an alternative. So I don't think there is an alternative. Like, if you have in other subsystems, sure. But if you have a subsystem that can be called from any context and can call into any context, then I don't see an alternative. In fact, I'm very happy that SRCU exists, because regular RCU does not allow you to call sleeping functions within the read critical sections. So SRCU is the only one. I'm not saying that this is the only solution, because for power sequencing, I'm not using it because you don't risk being called from atomic context. But in this case, it seemed to me that I cannot do it any other way. So do you agree that this needs to be addressed before we even go into OF implementation? Or yesterday you said that you want to start with the final part before you, in order to justify the changes to maintainers.
About device tree removal, there are so many aspects. One is the device tree representation. One is the removal itself, which triggers its own issues. And one is the various subsystems and drivers that are broken if you remove the overlays. So I think we can start with an implementation of device tree removal once we have some agreement on how to describe all the stuff in device tree source, and then also fix some of the subsystems that need to. Because if we need to fix everything before everything gets merged, it's never going to be done. So we have, in our use case, we have, I don't know, 5 subsystems involved. Okay, we need to fix those 5. But there are other 10s which are broken. Okay, when someone needs to unload stuff with those subsystems, they will need to fix them. Otherwise, I don't think it's really doable.
Have you looked at what the issue is in I2C?
No.
Okay, so the short story is that if you're removing an I2C adapter, sorry?
But we don't.
No, I mean, to me personally, like.
In our use case, we don't.
No, sure. That's fine.
I think it's kind of the point that Luca was mentioning, right? We will want to solve the problems for the cases that we have, and then if you have another case that causes another problem, it's another thing that needs to be solved. But if you
Sure. So I wanted to make a different points. I wanted to go into a theoretical question of how you fix an issue where you cannot really address the problem without changing all the users, or rather the problem is not fixable without changing the API, which was not the case with GPIO, fortunately. With I2C it is. It may be DSI in your case, for all I know. I'm just thinking, like, how do you approach it? Because it's gonna require much more effort, and it will be much riskier, because if you start changing every provider, you possibly introduce bugs and make them stop work, and then you need to go one by one and ask the people who have the hardware to test it. And I'm just aware that this is one of the issues that may arise when you try to fix it. And specific cases I2C, which you don't need, but it may very well be the problem for anything else that you use. And
you're right, but then what do we do?
No, just go case by case and fix it, I suppose. Or maybe you have a better solution. So I would love to hear it.
Yeah, so going case by case is what we are already doing for the device tree removal itself, which is already raising lots of cases. So I think I don't see a better approach. If there is one, I'd be glad to know. But as Thomas said, we are not having the need of removing an I2C adapter, so we are lucky. At some point, someone will, and so someone will have to address that.
Right.
I think so.
Okay. Any other points?
So, although I didn't attend your talk, so when you say about removing devices for via device tree, so is it about saving power or something like that you want to? Yeah.
No, the use case we have is a physically removable add-on, so that there is a main device which is standalone, it works standalone, and you can attach an add-on to provide more features. So via a connector that has an I2C bus and other stuff, so it connects I2C clients, definitely, and other components, some part of DRM, the DRM pipeline, and so on. So it's physically removing hardware.
It's a use case that I've seen already multiple times. You have, like, not a USB which is made to be hot unpluggable, but something that is designed to be static, like I2C, and then you have a GPIO. When you connect it, it goes high, and then the user space will know that, oh, someone connected something, so I need to act, and I need to see what's connected, read EEPROM memory, and see what the thing is that's been connected. Like, imagine if BeagleBone handled dynamic capes, where you attach a cape, and it comes up and gets new functions, then you disconnect it, and it's gone, and it's handled gracefully. This is the thing. So, like, dynamic static buses.
Exactly. Yeah. Yeah, it's basically the BeagleBone idea, but done at one time.
Probably my understanding of device tree has to evolve now. Because
it has. So yesterday, the discussion that Luca started was about how to handle device overlays at runtime, and how to describe such a connector in device tree, in the static device tree part and in the overlay part, which is actually quite an interesting problem.
Actually, when device tree started, it was like describe devices that are not dynamically detectable or not hot pluggable, basically. So that was my thinking. But yeah, these kind of scenarios are like hot pluggable. But yeah, we have the subsystems that work with the static and try to make them dynamic. It is a hard thing, yeah.
I think the device tree is not about whether it's out-pluggable or not out-pluggable. It's about whether it's discoverable or not. In our case, it's not discoverable, right? When with the hardware that's inside this add-on that Luca mentioned is a bunch of GSI bridges, I2C devices, whatnot, which are not discoverable. So device tree is a relevant fit for that. Because device tree is not about whether it's hot pluggable or not hot pluggable. Really.
It's a device tree implementation, but it's then considered hot plug in the beginning.
Right. Right.
How much of your preferred solution could actually be pushed down into the driver core? So your number one, what if any?
That's a good question, and I mentioned during a talk at the last year's Linux Plumbers that I'm thinking, it's not even working on, I'm considering a unified framework for provider consumer drivers,
or functions or something.
Or
like
yeah,
that.
so you would have a wrapper around your subsystem data and a wrapper around your driver data, and the entire thing with SRCU locking of API calls would be actually handled by that abstraction layer and not by each subsystem on its own. Because this is one of, I have a second talk about technical debt later in the afternoon, and one of the things that I want to touch upon is the fact that people come up with a need to introduce a new subsystem, and what they do, they just copy and paste something that's already existing, repeating the same mistakes, introducing even more technical debt, because then you have the same functionality implemented over and over in every subsystem, and I figured that the best approach would be to unify it. But making it unified has its own problems, because some subsystems will have much less strict requirements than others.
Yeah, but you're making an optional API, right? You're making additional functions somebody could use. You're not necessarily saying everybody must use these ones, right?
No, of course not. So I suggested it, and I remember that Greg Kroah-Hartman said that I should take 3 subsystems, the most that differ the most one from another, and try to unify those. That if that happens, then it will be much easier to prepare a unified interface for all of them, because it's highly likely that if you get 3 very different cases right, then others will be much easier. Please.
Could you go back to the previous slide? Yeah, so the 3 solutions, shall we say, I think they work okay for like the unbind solution, the unbind case, but for like module unloading, if you don't have like a flag or like nulling out the implementation pointer in your solution, then you can still call into callbacks that are no longer in memory when you unload the modules. So I think like the third case for read-only config structures, which get decopied, but you can't really copy the text portions, right?
No.
You only copy the function pointers. So that if you unload the module, and sure, all the devices get removed, but you might still have someone holding a reference to that provider and then does a callback, and then you call into something that is no longer there.
No. So look at the bar flop here. So this function is not in the provider driver.
Yes, what I'm saying is your solution works, the other ones maybe don't.
Ah, right, yes. This is why it's so good.
I mean, maybe we'll not be able to unload the drivers, because if you have the owner field set and someone uses the driver, there's this try module get, so you cannot unload the driver, basically.
So the answer is no. It's still correct, because what you should do, even if in the other 2 solutions, you should still be able to check that your device is still there. And this is still something that, like the NFC problem, like you may not need to do this whole SRCU stuff, but you still need to, when you enter your API function, take the read log, check if the device is still there, then while still being sure that it will not go from under you, at least the pointer, like the physical device can be unplugged, but then the lower level subsystem will handle that. You will call it, I don't know, you will send a USB request, it will come back with an error. but at least the pointer will still be there, and you are sure that it will stay until you release the read lock, after which you should not touch it, because then it can be unregistered and nulled. But with proper locking, I think this is something that is lacking from the majority of subsystems. Like the API calls may protect data, but they don't protect the device from being unregistered. So yeah, we have 1 minute left. So any last points, remarks? Cool. So thank you.
Can everybody hear me? Good. Okay, I think we'll start. So thank you everyone for attending this talk. This talk's about SD cards, why they wear out, and what you can do to improve the life and performance. My name's Andrew Murray, and I work for the Good Penguin. We're an embedded Linux consultancy, and we help Linux customers get Linux on their devices. But through doing this work, we often get customers come to us and complain about the apparent unreliability of SD cards. And some of these complaints might include just general data corruption, perhaps a file system gets corrupt unexpectedly, but also errors seen in kind of D-message as shown here. The other type of issue we see is customers complaining about poor performance. So perhaps they buy an SD card and the manufacturer says it can do 20 megabytes a second write speed, but they find that in actual use they don't get anywhere near that performance. And finally, and by far the most common complaint, is SD cards not lasting as long as people might expect. And that can often be quite a problem if your device is booting from an SD card, because when the SD card stops working, you can't remotely update it, and you have to kind of return it back to manufacturer. So we thought it'd be useful to take a closer look at SD cards to try and understand what's going on here and to give some better advice to our customers. So if we take a typical SD card, I say typical, but this is actually one I found in my attic. It's from 2007. I hope to find some photos of me at university on there, but as it turns out, and quite fit into this presentation, it was corrupt, so the passage of time didn't do it justice. But if we take the lid off, you can see some SD card connectors at the top. They obviously mate the SD card with the PC or the SD card reader. And the chip at the bottom is a flash memory chip, and that is where all your data is stored. The bit in between is an SD controller. It's a microcontroller, and that's really important. And what that does is it translates requests from the host that adhere to the kind of SD specification, and it relays those to NAND commands. And it also does some other really important jobs that take care of managing the life of the NAND chip. But the thing about flash memory is that this chip here is of type NAND, and NAND memory is inherently unreliable. But despite that, it's used everywhere, and it's used everywhere because it's cheap. We see it in things like eMMC, we see it in SSDs and USB mass storage devices, but we don't often associate unreliability with things like SSDs. And that's not because the fundamental NAND chip is different, it's because of how that NAND chip's used. So perhaps in an SSD there's a bit more redundancy, there's cache, there's different electronics, but fundamental to all of this is the root of your storage is unreliable NAND. I did actually find a Neo SD card, but I took the lid off and there really wasn't much inside, much to my surprise. But there is this kind of block at the top that has everything in it. It has the contacts on the outside, but inside it'll still have kind of NAND chip and it'll still have some kind of microcontroller. Now, in order to really understand why SD cards can wear out, we need to understand the kind of building block of NAND memory, which is the humble silicon transistor. I'm not an electronics person, so please forgive me if you are, but I hope the analogies will help explain how this works. This is a type of transistor called a MOSFET, a metal oxide semiconductor field effect transistor, and basically it's just a switch. Current will only flow between source and drain if voltage is applied to the control gate. The control gate is the switch, and when you press it, current flows. Now, this transistor is built on silicon. The silicon isn't really a great conductor. So in order to make the switch, the manufacturers will inject some impurities into the silicon in certain parts. And by injecting impurities, you can control or change the conductivity properties of the material. So around the source and the drain, they dope it, they inject an impurity such as phosphorus. And what's special about that is, compared to silicon atoms, it has an extra electron in its outer shell. And that extra electron can be used to carry current. It's not tied to any kind of bonds. We call that N-type doping. And I've represented it here with lots of happy electrons that are free to move around. The remainder of the substrate is P-type doped, and that's typically has an impurity such as boron, and that takes the opposite approach. So compared to silicon, it has one less electron in its outer shell. And that actually still improves conductivity, because what it does is, in the lattice of silicon atoms, there's now a gap where there's no bond, and that gap creates a hole, and electrons can jump from hole to hole. But compared to the N-type, it's not as good a conductor. And I've represented that with holes or circles. Now, the interesting thing about this is, on the boundary between the N and the P-type, the electrons from the N-type drift across into the P-type layer and fill those holes. And the problem with that is it creates what's known as a depletion area. It's a depletion area because the electrons that are in the holes can't be used to carry charge, because they're more stable holding that bond. And where they've come from, there's no electrons there anymore. So it acts as a kind of a boundary where electrons can't pass through very easily. And the effect of that is that this switch is off. Current isn't flowing. But if you apply voltage to the control gate, if you apply what's known as the threshold voltage, you can turn the transistor on. And the way it does this is, as voltage goes on the control gate, electrical charge is built up. It acts like a capacitor, because you have this oxide layer that's an insulator. And that draws the electrons towards it and gives it the energy. And the effect of that is this depletion layer moves down, and what you see is you now get a channel of electrons that can be used to conduct current. So as long as you apply a threshold voltage to the control gate, then magically current can now flow. Your transistor's on. So that's a kind of a basic MOSFET transistor. And a NAND cell is very similar to this, except we call it a floating gate MOSFET. And the difference is this extra kind of sandwich in between, where we have an additional conductive layer called a floating gate, and it's sandwiched in with insulators all around. And the really interesting thing about the floating gate is that's where your data is stored. If there's electrons on that floating gate, then we say the NAND cell is erased and the cell has a logic value of 1. Whereas if there's no electrons on that floating gate, then we say the cell is programmed and it has a value of 0. So literally your precious data is electrons trapped on a floating gate somewhere, which I find quite interesting. So how do you program the NAND? If this floating gate is surrounded by an insulator, how do you get the electrons on or off that? Well, you do that by applying a much larger voltage at the control gate. And this uses quantum effects that I don't understand, called Fowler-Nordheim tunneling, and due to the magic of quantum mechanics, electrons magically can pass across the insulator onto the floating gate. So you apply a large voltage to the control gate, and electrons move onto that floating gate, and now this NAND cell has a kind of logic value of 1. If you do the reverse and you put a negative voltage on the control gate, the opposite happens, and the electrons are drawn back into the substrate, given your floating gate, and this NAND cell a value of 0. So at this point, we've been able to program and erase our NAND cell. But how do you read the data on that? How do you know if there's electrons on that floating gate or not? Well, we have to remember that this is still a transistor and it still operates as a switch. But the interesting thing is the electrons on the floating gate, because they're negatively charged, they kind of interfere with the electric fields produced by the control gate. So when you apply the threshold voltage on the control gate, if there's electrons on the floating gate, the transistor won't turn on. So the effect of the electrons is that the more electrons on that gate, the higher the threshold voltage needs to be. And you can come up with like this kind of graph where the more electrons there are, the higher the threshold voltage has to be. So with this in mind, it's quite easy to say, well, I'll set a threshold voltage, and when I want to read the NAND, I'll apply the voltage to the gate. And if the transistor turns on, then I know there was no electrons on the gate. If it doesn't turn on, I know that there must be electrons on the gate, which meant that the voltage I applied wasn't high enough. And this is the principle behind single layer NAND, where you have one bit of information on a floating gate transistor. But manufacturers trying to improve the density of NAND chips, they decided it doesn't need to be binary, all electrons, all NAND, and actually it's an analog value. So perhaps you could say, well, if there's some electrons on, we'll have a different logic value. And that's exactly what they've done. And to read a floating gate that has, say, 2 bits of data per cell, you have to read the data, you apply a voltage. If the transistor doesn't turn on, you apply a slightly higher voltage. And by doing so, you can determine up to, say, in this case, 4 values. Now, the floating gate transistor isn't just used for NAND, it's also used for NOR. But the difference is how they're connected. And in the case of NAND, they're connected in series. So the drain from one transistor connects to the source of the next, and you form these long strings of transistors. But the organization creates a really significant side effect. So we know that, or the side effect is that you can only read and write in a granularity of a page size, which might be something like 32 kilobytes. And when you write, all you can do is you can change the 1 bits into 0 bits. But to go the other way around and to turn zeros back into ones, you have to erase the page. But due to the organization, you can't erase the page. You have to erase a whole collection of page, which we call a block. So you can write in a smaller granularity than you can erase. So to illustrate this, I've drawn, say, a block of NAND pages. I've colored them green to show that they're erased. And let's say that we want to program this and we write something to each one of those pages. So now we've used up our NAND and it's completely full. But what happens if we want to, say, change the data on the first page? How do we do that? Well, we're in a bit of a bind here because we can't, because in order to change the data, we have to erase that page first, but we can't. We have to instead erase the entire block. But the problem is that block has pages with data we want to keep. So a simple way to do this might be to make a note of all the pages that you do want to keep, mark the old pages not needed. Now you can erase the whole block. You can put the data back, including your changed data. Now clearly that works, but it's not very efficient because we wanted to write 1 page of data, but in order to do that, we actually wrote 9 pages because we had to write the 8 that were previously there and the 1 that's changed. And when this happens, we call this a write amplification effect, where the host asks to do one thing, but in order to achieve that, the underlying SD card controller has to do many more writes on the NAND. But clearly, this will be slower because you're doing more work, and as NAND has a limited life, this will obviously use that a lot quicker. So a more sensible approach would be to make those changes out of place. So when you want to change, for example, page A, you could just change it, put it on a new freshly erased block instead. So effectively, we have a kind of a log-based flash translation layer here, and we now have to keep a mapping between the kind of logical blocks that the host is saying they want to write to, and we have to know where in the NAND that is. And this works really well. But over time, as you keep replacing pages, you end up with this kind of mismatch of pages, some that aren't needed and some that are. And now if we want to change a page, we've run out of spare blocks. We've run out of freely erased blocks. So what we have to do is some housekeeping, and we have to combine all of the kind of unused pages, the pages we don't want anymore, into a single block so we can erase it. And this is what we call garbage collection. And we do a similar thing. We take all the good pages, we make a note of them. That clears some space. We can erase those blocks. We can write them back, and now we've got a new page. And in this scenario, we wanted to write 28 pages, but in order to do that, we wrote 37. So we've still got a kind of write amplification factor, but it's much better. It's 1 point something instead of 9 as it was before. So that's roughly how NAND works. But where does it go wrong? Well, if we take an actual photo of a NAND, this is a NAND floating gate cell, I think from the 90s, an AMD flash. You can clearly see the kind of N-channel going into the source and drain on the sides, the kind of mottled P layer. You can see a really thin kind of lighter colored, the oxide layer, and another one above that, and you have the floating gate and the control gate above that. But what happens is the electrons that are stored on that floating gate, they do have a habit of leaking out and disappearing, and that's not ideal, and that's partly why if you have, say, a NAND chip and you put some data on it and you come back to it in 10 years, it might not all be there. Also, the act of erasing and programming can put stresses on the NAND cell, and in particular, whilst electrons get onto the floating cell and come off, they can sometimes get trapped in that oxide. And the effect of losing or gaining electrons in this way affect that threshold voltage. And that's kind of okay because you can lose some electrons and that's fine. But as manufacturers try to put many more bits of data on a single cell, the kind of margins of error get smaller and smaller and smaller. Here's an example of TLC flash where you have 3 bits of data per cell. And obviously, you know, a few electrons makes a bigger difference in that case, and you might misread it as being 101 instead of 100. So for this reason, and mainly due to the oxide wear, NAND flash has a limited life, and the figures might look like for SLC NAND, where you have 1 bit per NAND cell, you might get around 10,000 as a minimum program erase cycles. With MLC, it might be 3,000, and with TLC, it might be 1,000. So the first thing we need to do is make sure that, obviously, we use those NAND cells evenly, and with the kind of approach we described, where you use like a log-based type of process, when you select a block to write to, you pick one that hasn't had much wear, and by doing that, you can try to spread the wear across your device. The other interesting thing about NAND is that because these NAND cells are all in a string connected in series, if you want to sample the data on one of those transistors, you have to turn on all the others in the string. And you do that by applying a much larger voltage. But every time you apply voltage to the NAND, you're effectively increasing the chances of electrons jumping onto that floating gate. So over time, with lots of reads, you get this read disturb issue where another floating gate somewhere else, its data might change. Likewise, as manufacturers are making NAND cells smaller and smaller, they get closer and closer together, and you kind of get this kind of cross-coupling effect. So when you erase one cell, you might affect the value in another. To some extent, ECC can be used to mitigate this. And if you look at the organization of NAND flash, you get like a main data area, and you get this extra outer band area where you can use to store ECC values. And if you look at any NAND data sheet, you'll get some description on the kind of required ECC requirements that are needed to achieve the reliability that the manufacturer claims. So as you can see now, the firmware in that microprocessor on the microcontroller on the SD card is really important. It has to do things like ECC, has to manage wear leveling, a flash translation layer, garbage collection, and all these kind of things. Its goal is to present a nice, friendly block interface that we all like to use. But it's a complete black box, and you've got absolutely no idea what happens, and it's kind of behind the veil of SD card manufacturers. But despite trying to present this uniform interface, some performance characteristics still can be seen. And what I've got here is a graph of 4 SD cards, and I've measured the throughput, the speed of a throughput when you write to the SD cards at different block sizes. And in all cases, the larger the block size you write, the faster the performance of the card. Also, generally, you tend to find that sequential access is much better than random access. So the point here is that even though you get a kind of a uniform block-based interface, it's not very uniform behind the scenes, and performance characteristics demonstrate that. So what we thought would be really cool to do is to take a kind of consumer SD card and write to it as much as we can to see how it fails. So we thought we'd see, firstly, how long it takes to break, how it breaks, and how our kind of write access patterns can adjust that time. So we started off with some Transcend 8 gig SD cards. They say on the packaging it's MLC flash, so we have some idea on what to expect. We set up one of these Raspberry Pi clusters. They have 4 Pico 02s on them. Each one's got an SD card, so we can run a test on each SD card. We also found these quite interesting micro SD to SD adapters, so we can also use full-size SD cards if we wanted to. On those Pis, we used software called FIO. It's open source software that allows you to perform I/O workloads. And what we did is we set it up so it would write the entire contents of the SD cards over and over and over again at the block layer, not at the file system layer, literally at the block layer. We did this differently for each card. So we had a test where we write in 0.5 megabyte blocks in a sequential fashion from beginning to end. And we also used varying block sizes, but in a random fashion. And with FIO, you can tell it to pick a random block, but use each block only once. And of course, we captured all the logs so we could figure out what happens when it goes wrong. We had a go at estimating the life, how long we thought this would last for. We've got an 8 gig SD card. We know that MLC should be able to do around 3,000 program erase cycles. So you could make the assumption that if we write to the entire card once, then we've probably programmed and erased each MLC NAND cell at least once. So if we multiply the two together, we felt that we would get around 21 terabytes before things start going wrong. And this TBW metric is a metric you might be familiar with that aims to describe the life of something that has flash memory in it. It's also worth noting that if you look at the kind of manufacturer's product information, they do express kind of endurance or lifetime in different ways. The card we've got is one on the left on the top, and there's no information about its endurance other than its MLC flash. But you often get endurance measured in terms of the application use. So on the top right is an example of how much video you can store, and obviously that's from a kind of file system application-specific way. And at the bottom, you can see sometimes they have expressed a figure in TBW, and some also just talk about the number of cycles the actual underlying flash can do. So then we set it up, and then we waited. And this wait was really painful, and this is where all the fear, uncertainty, and doubt kicked in, where you question everything you've done, and in fact, what we did here is we ended up with 3 clusters, and we initially started off with 32 gig cards, and when they weren't failing quick enough, we switched to 8 gig cards. When they weren't failing, we switched to 2 gig cards, and we changed the test each time. But it was a really good learning process, and we learned a great deal from doing this on how to do this type of testing. But anyway, eventually, enough cards failed, and we were able to produce this really beautiful graph. Now, what you can see is along the x-axis on the bottom is the amount of data we were able to write to the card before it failed. And where you see the kind of dotted line, that's the point where it failed. And then along the y-axis, you can see the throughput, how quickly we could write to the card for the given access patterns. And the black line in the middle is our 21 TBW expectation for how long it would last. And by the way, the whole graph is about 3 months. And actually, the red line, which represents the sequential 512K write, is actually still going, much to my frustration. And in fact, I can see if it's still going now. And as you can see, it's still happily going along. So I've been monitoring this thing on my phone and all the time. But I think this slide's really important because it shows that even though an SD card looks like a uniform block interface, how you write to it will affect both the performance and its endurance. And you can see that where you use sequential access, that's better than random. It lasts longer and it's faster. And also, when you use smaller block sizes, it's slower and doesn't last longer. And in my view, the reason for the latency and the difference in speed is because when you give a command to an SD card, it has to do some work. And the things that take time are programming and erasing. So if it takes longer because it's doing write amplification and garbage collection, then all that time is using those program erase cycles. And you see that in terms of a reduction in throughput, and you go through those cycles quicker. So how did it fail? Well, firstly, before it failed, on at least 3 of those cards, we saw some CRC errors in FIO, which is interesting because it means that the error wasn't detected anywhere, and it came to the application, and the application's like, something's gone wrong here. But if this wasn't FIO, and it was a file system, this is probably where you get corruption. And these didn't happen immediately before they failed. They happened sometime before. So that was really interesting. But when things did go wrong, we would get these 110 timeout errors, where a command is sent to the SD card, and the SD card's just like, sorry, can't do anything here. Sometimes we would get these intermittently, and things would carry on working, and sometimes they would fail continuously. And when they did fail, we'd get a kind of an I/O error, a kind of user space. Sometimes we'd get these kind of previous commands, never completed errors. And when we realized that an SD card wasn't ever going to work again, we pulled it out, or rebooted the cluster. And what we'd find is, again, we'd get the minus 110, I'm not responding error. And in some cases, it would detect the capacity of the card, and we'd get a device node, but every time we read and write to that device node, we'd get an error. And sometimes it wouldn't detect the card at all, so we wouldn't get a device node. When I did this testing, this wasn't what I expected to happen. My experience has mostly been on SanDisk SD cards, which have a very different kind of failure mode. And what they seem to do is they seem to detect they've gone wrong, and they go into this read-only mode. But they go into a read-only mode in a way where the SD card must just ignore any write requests and say, yep, I'm done. So they're effectively a read-only card, but the kernel doesn't know that. So when you write to it, you can write files, you can read them back, and thanks to the kernel's page cache, you're just reading from the page cache. You can even unmount it and remount it, and the data's still there. But it's only when you drop the file system caches or remove and reinsert the SD card that you realize all those changes aren't there anymore. And I think it's important to understand the failure mode of your SD card, because if you're building a product and it fails in this unexpected way, it might be, firstly, really hard to debug. But if you know how it fails, you can detect it, and you have a chance of doing something about it. So back to our testing, we ended up getting around 40 terabytes written on the sequential 512K test. And if you turn that into program array cycles, it's nearly 6,000. And that would assume that there's no write amplification at sequential 512K, which that might not be true. But from that, you can kind of get some sense of the write amplification for the different access sizes. And you can see that the smaller the write size, the worse the amplification is. I wanted to try and describe why smaller block sizes gives you worse amplification. And the best way I could come up with this is if you imagine kind of a mostly full card where you have kind of 3 blocks that aren't used, they'll probably be evenly distributed on the card. And so in the case here where we're writing at, say, the top line where we're writing at, say, 1 page at a time, then you need to bring 4 of those together before you have enough to create a new block. Whereas when you write to 2 blocks at a time, you only need to combine 2 blocks. So the question is, what can you do given this knowledge? Well, the first thing you need to do is you need to not write or read the SD card if you don't need to. You need to remove any unnecessary reading and writing. This will reduce the wear, but it'll also improve performance. And what's really easy to do is use the block layer statistics. If you cat proc disk stats, for example, for every block device, the kernel keeps a track of how much data has been written. And you can sample that, and you can see, oh, that's a surprise. And if it is, you can try and optimize that out by using things like block trace. And the type of activities you might do might be to remove unnecessary login, to maybe use a read-only file system, and maybe turn off kind of record and access times of files. In order to reduce write amplification, we obviously prefer using larger block sizes. And again, with the block layer statistics, the 2 statistics that are of interest are the write sectors, the amount of data you've written, and the number of I/O requests. And if you divide one by the other, you can get the kind of average write size. And you want that figure to be as high as possible. But when you know your average write size, it's really hard to do anything about it, because the path through the kernel is complex, and the kernel does a great job of abstracting that away and doing the best it can for you. And typically when your application writes somewhere, it writes to a file system, and any of those changes sits in the page caches. And then at some point in the future, the kernel decides how and when to write those dirty pages out. At this point, the block layer and the IO scheduler can do some magic in kind of combining write requests so that JSON write requests become bigger, and they can reorder them as needed. But the point here is that the kind of I/O access pattern at the block layer will be very different from that of your application. It's also worth looking at your file system. And what we found, a quick win for one customer was if you're using, say, exFAT or FAT, you have a cluster size, and that's the kind of minimum granularity of size that the file system writes. So if you increase that, then your average block size that you write is going to be bigger, and that can make a massive difference, and it's really easy to do. We spent a lot of time looking at I/O schedulers and the kind of various tunables. We had some good success with MQ deadline, and the particular issue we had was we had a device that records video streams, and there was multiple processes. And what we wanted the kernel to do is we wanted it to merge adjacent writes, but we needed the kernel to hold on to that data for long enough so there was something to merge with. And we found that using the MQ deadline and setting the parameter NR requests, it says to the kernel, look, you can have some more time. You know, the latency of the write isn't that important to us, but we just want you to have the best chance of combining writes. Obviously, if you're using direct I/O in your application or using things like Sync, well, that'll impact the kernel's ability to optimize things for you. One thing that's really interesting, I haven't actually tried this, but if you use block trace to capture I/O traffic from your application, you can actually use FIO to replay that. So if you're trying to iterate and make some changes, what you can do is you can run your application, record a block trace log, and then you can ask FIO to play it back really quickly. And then you can make some changes, and you can see how those changes affect it with a reproducible workload. The other thing that's really interesting is we looked at the garbage collection earlier on, and a lot of the reason for the write amplification was that the SD card controller is having to move around blocks of data that it thinks you need to keep. But in many cases, that might not be true. So if you delete a file in the file system, the NANDs and the SD card controller has no idea you deleted that file. And that's a problem because there's data on the NAND flash that's being preserved that doesn't need to be preserved, and that's causing write amplification. But a lot of file systems have like the discard property, and if you do that, when you delete files and when areas of the block device aren't used, it gives that information to the SD card controller, and it can mark that as something it doesn't need to keep. The other thing that's interesting is the amount of life you have in an SD card is really about the amount of NAND it has. Thanks to wear leveling, the larger the SD card, the longer it will last. So an easy win is always to buy a bigger card or look for one that has a higher TBW. And also, you know, if you don't need all that space, you don't need to use it, but you'll still get a benefit because of the wear leveling. It's probably worth speaking to the SD card manufacturers because they have a lot more information on how their controllers work. And they actually, in many cases, there are commands that you can issue that you can directly ask the SD card, how much life do you have left? And they have a wide range of things that's probably worth exploring. In terms of performance, what we found was if you use IOStat, you can look at the average write size, and you want that to be as high as possible. But what we find is when that's low, the SD card becomes a bit of a bottleneck, and as a result of that, utilization goes to close to 100, meaning that the SD card driver is being used all of the time. But the side effect of that can be the dirty pages in the kernel builds up to a point, and then the kernel says, hang on a minute, you know, you're producing dirty pages quicker than we can get rid of them. So the kernel will actually effectively throttle your application or use your application to write out those pages, and you get high I/O weight. So it's useful to look at IOStat and aim for a low utilization, a high average write size, and then you'll find that your average throughput goes up. And one of the last points I want to make is if you look at SD cards, SD card specification has a number of performance classes. You might often see the C10 or the 10 in the circle, and you get various video classes. And if you look at the SD card specification, which is publicly available, you'll actually find that many of the video classes make very specific assumptions about what needs to happen in order to get that kind of certification. They can include things like using a specific file system. Most generally always assumes FAT. It assumes a certain write size, normally 512K. It assumes, in the case of the video classes, it assumes that the kernel will actually issue commands. There's one that's, I think, like video class start mode. And the kernel just doesn't support these. So if you buy an SD card that says V30, meaning the performance in write and video, is not going to mean much in Linux because Linux doesn't issue those commands. What's interesting as well is there is a performance class, you might have seen A1, and these seem to be geared towards kind of mobile phones, which is why you tend to only really see them for micro SD cards. But they seem to be focused on being able to have lots of small write sizes. So the kind of underlying firmware in the controller is geared for lots of small writes. And actually, I've got a graph here. So this is an SD card that doesn't use the kind of A profile. The graph on the left is a brand new card, but that's not really representative because there's no garbage collection going on because there's loads of free blocks. But the right side is once you've used it for a bit. And you'll see that on a normal SD card, the sequential access is really fast and the random access is really slow. But if you use an A1 card, you'll find it's very different. And the point here is that the firmware on that card can really have an impact on the performance. So finding a card that meets your needs is really useful. Finally, we thought it'd be useful for our customers if, when things go wrong with SD cards, it would be nice to know how much data they've been written, what kind of a life that SD cards had. So we wrote an open source daemon that basically persistently logs the block stats for a specific device. And the idea, it's really simple, but the idea is that you can get some information. And we hope that this could be a starting point. So over time, we can add things like life estimation, or we can perhaps predict just before a card's going to fail. So we put that on GitHub, and any kind of input or involvement we'd really appreciate. So to summarize then, the kind of key take-home messages here is that how you use the SD card, the access patterns will really have an impact on its performance and its life. Sequential large access is always better, and quite often sequential accesses are too, but it depends on the SD card. If you can always get a bigger card than you need, because it will last longer, I would ignore kind of performance classes and measure a card yourself. Always kind of measure at the low block level layer and try and optimize at that, and choose an SD card wisely. So that's my talk. If you've got any questions, feel free to let me know. I don't know how to turn it on. I'll leave that with you.
Hey.
Hello.
So, thanks for the great talk. It's one of the most interesting one I attended to. I have two questions. Although the second question I think I got to answer already, but I'll anyhow ask. So first one is for your tests you did you read the I think with MMC utils you can read, I think it's called XCSD or something like that, registers?
Yeah, so for eMMC you get that, and that's part of the specification, but not for SD cards. It's only certain manufacturers that will have their own commands that you can probe that information, but generally SD cards you don't get that.
Do you know if this is really reliable? These registers? How do they?
I think so, because they come from an understanding of the firmware in the SD card. So so certainly if it's there, it's worth relying on or using.
Okay, and the second question is related to the evaluation of the lifetime of I'm interested in eMMC. I guess it's the same applies for SD card. Is it so parsing this block disk stats?
Yeah, so that's applicable for any block device.
So that's what Krill counter does, or?
Yes, yeah. Because if you look at block stats, obviously if you reboot the machine, they go back to 0, and you want to kind of associate the block count with a specific device that maybe have a serial number. And also those counters do overflow over time, so curl counter deals with that too.
So it accumulates the...
Yeah.
Okay, great. Thanks.
Any other questions?
Yeah, 2 questions also, please. You kind of touched on it there about using an oversized SD card. I wonder, would there be an advantage, did you perhaps examine it, about using a portion, just say, I don't know, 75, 80% of the SD card, leaving a portion unpartitioned?
Yeah, so that's beneficial. And it doesn't matter if it's an unpartitioned space or if you've got a file system that can, when you don't use the space, it definitely uses it. But the point is that from the perspective of the micro controller in the SD card, it wants to think those NAND blocks are free. So obviously, if it's unpartitioned and if it's never been written to, then that's fine. There's a command I think called block discard, which is a way of saying these blocks aren't used. So obviously, doing that on that kind of area would be really useful because you only have to write to that unpartitioned bit once, and then the SD card will think that there's data in there it needs to keep. So that's really crucial as well, I think.
Okay, thanks very much. And second question then, you mentioned about how the SD card records a map of which kind of pages are in use.
Yeah.
Is that map stored on the same medium that...
I mean, it has to be somewhere persistently, but I don't know. I mean, this is black magic from the vendors, and really, these, to some degree, guesses for how it actually works. But I suspect there will be some storage used for keeping that.
Okay. And if that gets corrupted, obviously, then that's the whole
card. Game over.
All right.
Really good question, actually.
All right, thank you.
Yeah, hello. Did you try to use Flashbench to know whether how many open AU you had on your SD cards?
I did look at that a long time ago, and I don't know how relevant that is to today's NAND, because I know that's quite old, isn't it? So the concept here is that if you consider an SD card controller, it's a microcontroller. It's got limited, RAM, for example, and I think the view was that when you're doing kind of random access for that kind of garbage collection and housekeeping, it does it on a certain area, and it has a sense that you have these open allocation units. But then when you move over here, you have to do the housekeeping, tidy that up, and some cards have more open AUs, access units that you can use. But I don't know how true that is now. I didn't go too far down that road, but it would be really interesting if there was someone here that works for an SD card manufacturer or someone that could open source the firmware on the microcontroller, on the SD cards would be really useful. But yeah, a lot of it is guesswork really. So I did play with that, but I didn't really come to any fruitful conclusions.
Have you looked at benchmarking retention after exceeding the rated number of cycles for the...
It would be interesting to do that, but my experience of doing this is things take a really long time. So I don't know. It's interesting, actually. I've seen graphs from vendors where you kind of get a graph that shows retention, and the retention depends on not only the wear of that individual NAND cell, but also the temperature as well. It would be interesting to do that, but I've not had a reason to do that yet.
So your test, about how long does it... I mean, are you reading back and verifying exactly what's there?
What, in these tests?
Yeah.
Yeah, that's what we do. So FIO, we
just immediately right after then?
So there's some options in FIO, and what we didn't want to do is read it back straight away in case the SD card has some kind of cache on it. So I think we told it to wait like at least 100 megabytes before it starts reading it back. So we read back everything that we wrote, but not necessarily straight away.
Thank you.
Hello.
Hello. Yeah, so have you done any tests where the flash itself was subjected to a higher temperature and then see if it wears out faster that way or it affects it?
I haven't, but I think it would. But yes, no, I've not done that. That
Or
would
maybe
be
a colder
interesting next
temperature would make it more resistant, or things like that.
I think so, yeah. I think that's just. I guess generally the higher temperature things have more energy and they can move about more and escape. Yeah. I've got a question at the back. If we could get the microphone over there.
Yeah. The graph that you showed halfway through, showing your results, there were some changes in throughput, like at different sections for at least 2 of the lines, and I was just wondering what that is. You see it on the yellow and red lines.
I've seen this on other tests and I've done. It's like this kind of bimodal thing, and I haven't come up with a good explanation. And the thing you have to remember is each one of those dots isn't a single read, it's a read of an entire SD card. So that's like a change in throughput over quite a long period of time. I could only come up with guesses, so I didn't make any comments. I mean, it's possible that SD cards improve performance by having multiple flash dies, and the performance of each die might be slightly different. So maybe generally you've got a mix from the two, but occasionally you use the slower one more often. But it's weird how it goes down, it stays down, and it goes up. The other thoughts were it could be related to the kind of garbage collection, and it's kind of got into a bit of a state where it's having to keep doing the same thing over again, and then it kind of recovers from that, and then it's more efficient. That's probably the most likely one. The other really interesting thing I found about this graph was on each case, you see, particularly with the slower ones, you see a slight degradation in performance for each of them, but the sequential one, you get an increase in performance. And I think the reason why is that when NAND cells wear out, erasers take longer, but programs are quicker. So I think when you're doing more erasers because you've got the amplification, you see that in reduction in throughput. But for the sequential mode, where mostly you're in programs, you see that. It's just a theory, but it would have been interesting to do the same test, but with an actual NAND chip. And then you could measure this stuff on the scope a lot more. But I thought it'd be useful to do it from Linux as well, because that's how we use it and come across these issues. Any other questions? Okay, well, thank you, everybody. Thank you.
Thanks for the great talk.
Oh, thank you. Much appreciated.
So are each of those lines only one SD card?
Yes.
Okay.
Yeah.
Yeah, that was the thing I was confused about, because I was like, oh, well, if you had multiple SD cards, why are all of them going?
Oh, no, yeah, so each card had one test, yeah. We did it for
Testing. Oh, yeah. Can you hear me all right? Folks, it's 3:13. We'll wait a couple more minutes until we can get started. Okay, good afternoon, folks. It's 3:15. Let's get started. We have a lot to cover. Who are we? We are Texas Instruments. We love open source. We like to contribute more. We'd like to work more. And our motto is upstream first. And that's exactly why we are here today. A little bit about me and my co-author. I work in the systems domain with Texas Instruments for about 2 years now. And my current project is about boot time optimization. Whereas Samya has also been working with Texas Instruments for about 2 years, and he mainly leads the RTOS stack. This is the overview of the presentation right now. So what is our problem statement? It's that we have too many requirements for a little ARM core to be able to manage. So what do we need is we need a heterogeneous system. And what I've shown right now is a simple automotive infotainment use case where you want an audio chime in about 200 milliseconds. You want an early splash screen in about 500 milliseconds. And finally, a full graphical application in about 1.5 seconds. Now, this is obviously not possible with one core. So how do we manage to have heterogeneous, a boot which includes heterogeneous system in its early boot scenario? Okay. I will run through the existing sequence, and I will highlight what did not work for us, and then what we've tried out at Texas Instruments. And then finally, we can have some thoughts, and there were some surprises to us that we can collaborate upon. Just to give a reference as to the platform that I'm talking about is the Texas Instruments' AM62P. It's a quad-core Cortex A53 application core with 2 Cortex R5s running. Now, it's important that I highlight that one's called the DM, the device manager, and one's the MCU. The microcontroller application will be running off the MCU Cortex R5. We can note that the multiple boot media that we support is OSPI, NOR, NAND, and eMMC, right? So the typical boot sequence, once you turn on the power, is your PMIC is up, and I will go through each of these blocks in detail later. You have the PMIC which powers the SoC, then you jump to ROM, and then you go into your bootloader. In our case, one stage runs at in the R5 core, and one in the A50, and the rest will be running on the A53 core. And once you hit U-boot, that's when we can start all our heterogeneous applications. Then finally, the kernel, and then the user space. So from the time you have power coming in, how does your system get powered on? Is through the power management IC or the PMIC. Right? It handles voltage regulation, power monitoring, and giving the power essentially to the rails of the entire system. Once the power is up, what happens in a simplified manner, I just say ROM comes up. Now ROM initializes a bunch of resources to initialize the next core. Now, in the K3 architecture of TI, we always boot off the R5. So we enable anything and everything that is required for the DM-R5 that I mentioned earlier for it to boot. Now, I want to highlight that the ROM has device drivers for the specific boot media that we have. So it has to open these drivers, it has to initialize the boot media, then load the binaries, and then jump to the bootloader. The typical bootloader that we are all used to is the U-boot. And in our case, R5 SPL, since it's running off the R5, it's the first stage of the bootloader, where we typically do not have DDR up and running. So what do we have to contend with is a small on-chip RAM. In our case, it's 256 KB. So the main job of R5 SPL is to start the DDR so that all our other cores and all the other binaries can be loaded. Also, again, in the K3 architecture of TI, TFA is the one that starts the ARM core. It's essentially, it fixates itself as the EL3 monitor handler. So once R5 SPL is done, you jump to your TFA or trusted firmware ARM. And from there, we jump to Opti, which is the non-secure Linux compartment to the TFA. From Opti, we load into A53 SPL, where we have more functionality, and it's running off the A53. Your core is finally running at best. So from there, we jump to U-boot proper, which everybody, I'm hoping, is familiar with, where you have a wide variety of functionality available for you to boot into multiple medias. You can have a lot of functionality there. And from here, you parse the device tree, you parse the kernel, and then finally load into your kernel, which goes through a multi-threaded initialization. We have 4 cores. We have to use all of them, right? It initializes all our drivers. It initializes the entire system. And from now on, this is the system you're going to be working with. At the end of the kernel is your process ID 1, which actually starts your file system, which lets you work on your user space applications. Now, all of this is very cumbersome, and too many stages are going on there. The U-boot that I highlighted is already about 6 seconds into the whole system, and that's not enough for the applications that we have, right? So what did we do? We said, we'll make our own bootloader. Because the current bootloader, we had to pivot from it because there's a lot of upstream problems going on right now, and we decided to talk with the community and as to how to be able to do this, right? So for now, we have implemented a special bootloader, and we have other multiple optimizations going on. So this is the optimized sequence that I'll be talking about, and I also like to refer to a talk by Qasim which says, how do we standardize these early access to hardware, right? So we still have our PMIC, you still need your power, but as funny as it sounds, it just needs to do it faster. That could mean the difference between your SoC starting from 15 milliseconds to 45 milliseconds to 100 milliseconds, and you've already lost some of your KPIs, right? So the choice of PMIC is the first step. Now, the next thing is, if you remember, I said that ROM initializes the device drivers that are required for the boot media. So why do you want to waste this time by closing it and letting the later stage open it again? So what we've decided to do is we initialize the boot peripherals, and we leave it open so that the next stage can directly use it under the assumption that it is already open, which SPL does not let us do at this point. Another cool thing that we've done at Text Instruments is that in a typical use case of OSPI NOR, we are able to shift into the 80-80-80 mode and at 1666 megahertz. Typically, we work with a lesser megahertz, which is about 42 to 50 megahertz, but it's something called the OSPI 5 tuning, if you're familiar with the jargon, right, to allow us maximum throughput right from ROM. For the next stages, I will let Soumya, the leader of the RTOS stack, take over.
Hello, everyone. I guess I'm audible. So, yeah, so as Asus told a bunch of problems that we are seeing with respect to SPL, the init time, and all stuff that we have with respect to SPL. In a typical heterogeneous system, right, you see like when you boot, and your first bootloader comes, say for SPL, you have a very small on-chip RAM because of various reasons. You keep a smaller RAM. You don't have DDR access. You have to initialize DDR. So SPL does it for us today. We do have it. But once you boot that, right, there are a bunch of scenarios like you have so many peripherals or the firewalls or something which are already open by ROM for you, and you are not able to reuse it at a later stage. And you are not able to use the boot peripherals at its maximum, throughput or maximum, the boot drivers that give you, already initialized by the ROM. You're not able to use it at its maximum capability. You again, at the later stage, you again go through the same process of initializing again. So if you compare, what we have here in TI is a secondary bootloader. And we do boot from a smaller chip, on-chip RAM, just like SPL. But later, it does a DRM initialization, the DRAM initialization to make and up the DDR. But later, what it does is, instead of initializing all the boot peripherals again, it reutilizes the initialized thing that is already done by ROM. And it will start copying the first image, that is the stage 2 bootloader, from the flash device and put it in the DDR. And why we have staging here? Okay. So you may ask that why do we require staging? We could have done it in the same thing. It's because normally if you see today, we can have one concept is like you are in a production software, right? You always want one type of boot media, one primary boot media and a fallback boot media, which you will always boot from. So you don't require like, okay, I will have bunch of support of different boot medias in my bootloader. So what you can do is like, I will just have the bootloader for this boot media. So with the TI's SBL, you can have a particular bootloader that is only interested towards this boot media, whatever you are interested in. So whatever you want to have. So what it does is like, it still reutilizes the initialized boot peripheral that you have from the ROM and keeps on continuing from stage 1 to stage 2. And apart from that, in all this scenario, in your heterogeneous SOC, you have a requirement of power and clock control. So when all the other hosts are about to be booted, and once they boot, they will start requiring access to different peripherals, and they will start requiring access to clocks, the powers, and all. So you have, anyway, we talk about SAP firmware, or what we call in TI is a device manager that overall controls the power management, the clock control, and all. So before all cores boot, you need to have that thing available in your system. So what we did is, with this stage 2 bootloader that we have that device manager plus bootloading happening at the same time in a multi-threaded context. So you have your clock control, the power control all available at the same time, and also you're booting different cores together with it. Now, next thing is, in a normal SPL flow, you will expect that, okay, my remote cores will be booted just at the U-boot stage, or when Linux boots up, it does rproc and starts booting the remote cores. Or you can have some hacks at a higher, earlier stage to boot those, but still, in a very time-critical system where you want to have use cases like early splash, early chime, where you want MCU to come up earlier and do the hardware access and keep it in initialized state, and you can give those things available to high-level OS like Linux later. So you can boot MCU in this context by stage 2 bootloader earlier in the system, so that all your peripherals access like display or audio for chime and all are already initialized and in the system, and you're able to give a smooth user experience. Next, there are a bunch of optimizations that we did with respect to the kernel. I'll ask Ashish to take over.
Now the bootloader is done, that's fine and dandy, but now the fun part is the Linux and the file system, right? We always think Linux takes a lot of time. Now, how do we do that? The boring answer is reduce your logs and remove the configurations that you have. But the problem that is, what configurations do you want to remove? We don't know that, right? It's a customer-dependent thing. So I've highlighted a couple of configurations that we had to remove and directly affected us by a lot. But please understand that some of these have security implications. Some of these are required, maybe. I mean, not these guys, but understand the system that you're trying to optimize. For example, RO data works with, has security implications and not just remove things. Right? Some things like MMC, SPY, debug FS is just a file system for debugging. We don't really need that. But you're welcome to go to the link that we have to find out the entire configuration file that we've developed for an early boot scenario, where we've highlighted what configuration takes how much time in our system. So now the file system typically is packaged as an init ramfs with our kernel, so that we can save some time and boot it as an init ramfs. For the purpose of that, we've chosen sysv init as our init manager. Let's not get into the whole system v init or system d conversation here, but it worked well for us. Okay, we understand it a little better than system d at this point. So now that your kernel is small, it's light, you've hit process ID 1, and your file system is ready. So in system v init, we have something called run levels, which is RCs 1, 2, 5, and S and Ds. Out of which RC5 is the one that's responsible during your multi-user login. Now, in that, what you do is you go check if a service is required or not, supposing UDEV or Ethernet or things like that, and you remove things that you do not need. Okay. Another experiment that we tried is, what kind of file system do you want? Do you want ext4? Do you want UBIFS? Or do you want squashfs? Now, for those who don't know such file systems, I recommend going reading it. I want to highlight that UBIFS in particular is very interesting, where UBI is a software layer that's used for volume management and wear leveling. Okay, and UBI is something that scales linearly, whereas UBIFS, the file system based off it, scales logarithmically. What it means that the more size you have, it still saturates after a while. But at the end of the day, UBIFS also scales linearly, since your software stack also scales linearly. Okay. Why is this important? Because this is the results that we've achieved from trying out different file systems. The same file system that we have, the way you package it as an ext4, UBIFS, or even squashfs, these are the results you get. Now, ext4 to UBIFS is a surprise to us, because UBIFS is known to have faster mount times. And yet, from the graph that you can, from the table, you can see that it adds 48 milliseconds to ext4. Now, that is very surprising to us, and we've not been able to figure out why. And the compression is not that much, so it's only 7 MB. It should have been fine. squashfs, on the other hand, is completely understandable. You're compromising mount times for smaller kernel sizes. That squashfs that you see 5 MB is squashed quite a lot, right? And at the end of the day, this is what results we've achieved. I think. Yeah. So on the left is the optimized sequence, and then on the right is still the regular one, which is going and taking its own sweet time. Right. We can still further improve this a little bit, but I wanted to show some logs that are going on, and you can see how much time this takes. Right. We booted 12 times, I don't know, 15 times by now. These are some of the more profiling that we've done, and it's important to profile these systems. You want to know exactly how much time these take, and these have been done using GPIOs and logic analyzers. Okay, you can see that the regular boot sequence, I've not mentioned it, I guess, it's about 25 seconds, whereas our optimization is done within 1 second, 1070 to be perfect. And you can notice that our MCU application, our chime or display, is already up and within 125 milliseconds. Right? So at the end of the day, all of these optimizations are nice, but how do we get them back into SPL? How do you get them back to U-boot? What happens is that boot time optimization is not a new concept. Everyone's done this. Now, how do we proliferate it back into the community, right? So how do we get what we've done back? How do we get the assumption that a previous stage has worked on the device driver, so you don't have to waste time resetting it and opening it again. That's a couple of questions that you're asking. And a file system, it's very bare bones at some point. I'll be honest, it's practically unusable except for the things that you really want to do. I guess I didn't mention that, but once you have the tiny file system in there and your graphical application is running, that's when you shift to a full file system after a while to have all your complete extended functionality in, right? So how does this bare bones file system sit with building Yocto recipes? How do we maintain these guys? And finally, if somebody is knowledgeable here, we'd like to understand why, if we're doing the right thing with UBIFS or ext4, or we should try something else altogether, right? We also had another look at CRAMFS as another file system there, but we didn't have any measurements for that. These are some of the references that we've had. And if anybody's interested in recreating the environment we've had, you can go order the boards, you can try all the commands. We've got how-to guides as to what time we're spending. I'm opening it for Q&A. Yeah, thank you. Does anybody have any questions?
Thank you. Thanks for the presentation.
Yeah.
It's just an hypothesis about the mount time with SquashFS. As far as I'm, thank you. As far as I know, you can really notice the difference in the latency in a scenario where you are reading your file system, either if it's an initramfs or your actual root file system from the disk. And considering that you're compressing it, you are doing fewer reads from the disk. And in that specific scenario, you could notice decrease in mount time.
Correct. But
and in your case, so what was, in your case, I presume the initramfs, the file system was already shipped in the kernel binary?
Correct.
Right, because that would make sense to me, because in that case you completely discard this idea where reading from the disk is lower, so the advantage kind of disappears.
Correct.
But anyway, I was surprised too to see even though you cut the size like in half or even more, and still you got a few milliseconds.
Oh, yeah.
I would be disappointed as well.
Exactly. It's all about decompression and compression times, right? The more you decompress it, the more the decompression time also will be.
Have you tried with LZNO?
Yeah, I believe, oh no, we did not try that. I think we had about 4 things to try. We tried 2 and we decided, oh no, this is too bad. Yes. Fine, we'll try out LZO.
Thanks.
Yeah.
I guess I'm going to follow up a little bit on SquashFS as well. There are settings around whether you decompress directly to page cache, whether you decompress into a temporary buffer, and then copy it over to page cache, and also whether you're doing it single-threaded, multi-threaded. Did you investigate how you're actually using SquashFS in kernel?
No, I did not. Let me just write that down. I did not have we did not have too much time to get into that, or the expertise, to be honest with you. So, but I will look into that.
All right.
So my question goes on splash screens. So going back to the boot like sequence.
The optimized one or the regular one?
Yeah, we can start with the regular one. So usually you have one splash screen for the U-boot and another for the kernel. And then between changes from the U-boot to the kernel, you have like a black screen between them. And then when you change to the kernel to the user space where your application lives, you also has a black screen between them.
Yeah.
So in your fast sequence, do you get rid of those black screens?
Yep. Yep. So even you can get rid of that in case of SPL. There is something called simple frame buffer thing, and you can allocate the same frame buffer space, keep on until the kernel, that it can reutilize it. So it's there in TI platform. We have, I guess it's been upstream that we don't see that black screen. And with respect to the RTOS, basically the splash is there. The same frame buffer can be occupied by the kernel also. It can just keep on relaying the same frame data. So it's all, so it's the same thing. It's just like in the SPL flow, you have a U-boot doing the splash. In case of the SBL, it's the MCU or whoever is the bootloader that can do.
Thank you.
Any other questions? Going once, going twice. Yeah, thank you. Oh yeah, thank you.
Great presentation.
Yeah.
Mic check. Okay, let's get started then. Welcome everyone to the last session of the conference. Today I'll be talking about second source component probing on device tree platforms. My name is Chen-Yu Tsai. I work on the kernel for Chrome OS. So just a disclaimer. The examples mentioned will mainly focus on Chrome OS devices because that's just what I have. I've done some experiments and I've posted some patches, but this is pretty much an unsolved problem. So I'll give a quick background on what we're dealing with, the current status of the things in the kernel, and some proposals of how I'm solving various parts of the problem. So first of all, component second sourcing. So what is second sourcing? So when a vendor designs a device such as a laptop, they'll select various components for their design, and sometimes multiple sources will be chosen for a given component. Or the component could be swapped out later on because of shortages or end of life of a certain component. The components are supposedly functionally similar, but that's only on the hardware end. They provide the same function. They could be pin compatible, most likely not. Unless they are like modularized through a common connector for things such as a display panel, your touchpad, your touchscreen. And because they are different components from different vendors, they will require different power sequencing and different drivers. And the hardware designers expect everything to be solved through software. Device trees. I think everyone here pretty much knows what a device tree is. It's a minimal description of non-discoverable hardware for your system. It's enough information for the operating system to enable and use the device. It doesn't include any enumerable devices, such as USB, PCI Express, SDIO, that sort of thing, unless these devices have non-discoverable properties, such as a regulator supply or GPIOs that need to be toggled for them to come to life. So in the device tree, every device node would have a compatible string, and that compatible string basically identifies which component this is. However, for the root node, the compatible string really doesn't do anything in Linux, but some bootloaders will use that compatible string to basically identify what device this whole device tree is for. It's kind of a reverse mapping. And so one device tree could be used for multiple devices if they look identical to Linux. So you could also have different SKUs mapping to different compatible strings, and if you have variations in your components, then you get more different compatible strings. There's an example here that shows the MT8186 Core Solap family of devices, which has this device called Magneton, and which has like 2 different SKUs. The Chrome OS bootloader. So the Chrome OS bootloader uses fit images to basically deliver the kernel. The fit image includes one kernel image, one kernel binary, and a whole bunch of device trees, and maybe some overlays. And also a bunch of configurations. One configuration maps to one kernel image plus one base device tree, and 0 or more overlays. And the configuration has a compatible string tied to it, and that currently is derived from the board level compatible string. And for us, the device trees are always bundled with the kernel and not the firmware. And so the bootloader knows what device it is. It knows the family. So for instance, it could know that it is the device Kakadu. And then depending on the design, it could read an ADC for a resistor value or some GPIO strappings, or maybe some EEPROM to figure out what the SKU number is, what the revision is. And then the bootloader generates a list of compatible strings to try. It goes through the fit image and tries to match one of its compatible strings to one of the configurations in the fit image. And that's basically how the Chrome OS bootloader figures out like which device tree to use. Some related work. Elliot had a talk yesterday about shipping multiple device trees. It's a similar problem, but how we look up which device tree to use is slightly different. So our goal is to reduce the overall fit image. You could either reduce the kernel size or reduce the number of device trees bundled or reduce the sizes of the device trees bundled. So this talk basically looks at decreasing either the number of device trees or the sizes of the device trees. And maybe try to move away from having to describe all the SKUs and the revisions in the compatible strings. So the current status, we have various design variations. So in some devices, we have the manufacturer switching between different types of trackpads or touchscreens. And every time the manufacturer introduces a new trackpad, they will basically add a new device node to the existing device tree. And since the new component's I2C address does not conflict with the existing ones, they will simply add the new device node, and they won't bother with allocating a new SKU identifier for it. And so you get this device tree which has 3 or 4 touchscreens or trackpads on the same I2C bus, but on the actual device, only one of them actually exists. And this allows the hardware vendors to basically swap around modules without having to reprogram either the bootloader or the EEPROM that contains like identification numbers for the model. And that's kind of what we already have in production. It's already seen in devices on the market. But that only covers like the simple situation where you don't have conflicts. And recently, a manufacturer introduced a new trackpad that has an address conflict with existing components. Now, in this case, you can't add two device nodes with the same address because the device tree compiler would complain that either you have overriding device nodes or you would have to rename the device node and then the DT maintainers would yell at you. So basically, what we did was we allocated a new SKU ID for this new variant. And now you have 2 separate device trees, one with the old trackpads and the new device tree with just one trackpad, the new one. And now you have like basically 2 copies of almost identical device trees. And the third thing that we have is hard to discover component changes. So I2C components you can sort of probe. You can basically send a transfer to that address, and if it replies, then, well, the device is there, and maybe it's the correct one. But for things like DSI panels or cameras that require certain power sequencing commands, it's hard to actually probe these because you have to know ahead of time which sequence of commands to actually send. And so basically you have to have different SKU IDs and then different device trees. And so again, you end up with 2 almost identical device trees. Now the last class is innumerable component changes that basically have identical device trees, but for some other reason, internally they have to allocate a new SKU ID for it, and therefore you kind of end up with 2 device trees that have completely matching information. And so that's basically what we have right now. It's kind of different workarounds for different situations, and it ends up causing like tens of device trees for one family of device, and we'd like to like reduce the number. So now I'll go through some of the solutions or proposals that solve one aspect of the problem. So for the device for I2C components that don't have conflicting addresses, I2C bus is not discoverable. There's no enumeration. The expectation is you describe the device in the device tree. And it's possible to probe the device. So if you tell it that, okay, there's a trackpad at a given address, you can send a simple transfer, and if it replies, then okay, maybe the trackpad is there. But there's no guarantee that the device that actually responded to you is the device that you are expecting. Most I2C components do not have a chip ID that you can verify. The only exception that I know of is I2C HID devices. They provide a fixed format descriptor. However, the descriptor is not always at the same register address. So the only stable way of probing things is just to send a simple transfer. And so what we currently have is we have maybe 3 or 4 trackpad nodes on the I2C bus, and those are all enabled. And so the kernel goes in and binds each device to their respective drivers, and the driver probes, and maybe the driver tries to verify that the device actually exists. And somewhere along the line, all the trackpad drivers got changed to synchronous probing. So now all these drivers probe at the same time. However, your trackpad might need a regulator supply, it might need a GPIO line, it might need an interrupt line, and these become shared resources within the kernel. And so if you have 3 drivers probing at the same time and all requesting the same resources, for regulators, you can share them, GPIOs, maybe, maybe not. Interrupts, maybe, maybe not. But it requires, like, you have to fix all the drivers to make them share the resource, and they're typically not meant to be shared. So what normally happens is you have 3 drivers probing at the same time. One of them requests the resource successfully, and the other 2 fail. And then the first one probes the device, and then the device is not there, it doesn't respond, and then it fails, and then you have nothing. So that basically is kind of flaky. So you basically have maybe one will successfully probe, or maybe none of them will. And we've basically worked around it by moving some resources up a level into the I2C bus node, and some, like the regulators, we just set them to always on. And for the interrupts, in the drivers, we've moved the request IRQ call to after the I2C probe, I2C transfer probing. And these are all workarounds, especially the device tree where we move the resources up one level. That does not match the actual hardware. Well, we've been asked, can't you do probing in firmware? And sure, that's doable. The ThinkPad X13S with the Qualcomm SoC actually does this. But then it doesn't pass the result to the OS if you're wanting to boot Linux. And either the firmware has to pass the result to Linux in some other fashion, or it has to modify the device tree to basically hook up or add the node that it probed. And in some cases, you might not want to do this. You might not want to tie your firmware to your kernel in such a tight way, because when you ship the device, either your bindings might not have been vetted or reviewed by upstream. Your devices might have been under embargo and you couldn't have sent patches. Or you had some downstream kernel tree and then that doesn't match upstream. In addition, firmware should just do enough to get you to whatever you're booting, and it shouldn't really do too much to like probe the system hardware. Basically, anything that can be initialized by the operating system, it should leave to the operating system. And also, in some cases, for Chrome OS, part of the firmware is read-only. It cannot be updated once it leaves the factory. So in this case, I've put together basically a platform device driver which basically tries to probe all the trackpads or your touch screens or whatever. So what you do is you mark the trackpads in the device tree as disabled or failed needs probe. And this driver will basically go through the device tree and see which nodes need probing, and it will probe them one by one and do power sequencing as needed. And if optimized, it could just do the power sequencing once, and you would power everything on and do the probe quickly. And then once it finds one that it actually exists, it will enable the device in the device tree and pass it on to the kernel and let the kernel do its usual thing. And the patches are on the mailing list, and that works pretty well. I still need to add like GPIO and regulator support for this series. So that's one case where these are targeted only at I2C devices that don't have address conflicts. If you do have a conflict, then it gets terribly complicated. You have to have different device trees. So if you do have some sort of identifier from the firmware or from your device in hardware that tells you which variant this hardware that you're booting on is, then you could presumably know which device is currently on your hardware. So in this case, we could say list all the possible components in the device tree and mark them as disabled. And then there's a platform driver that reads the identifier, and then it knows which components to enable either by compatible string or by path. Presumably by compatible string is better. There are also patches for this. The one thing that we've heard from the DT maintainers is do not generate the device nodes on the fly. You should have them in the device tree and just disabled. And then your driver or whatever can go through and enable the correct one. So this lets you basically merge different SKUs into the one common device tree. However, it pushes some of this logic into the kernel. And if you're, for example, merging multiple panels or like camera sensors, which are part of a device tree graph, an OF graph, the device tree compiler will now complain that you have one or more graph endpoints that does not have a remote endpoint, which basically it will complain that you have an incomplete graph. And I think we've talked to Christoph a bit earlier about this, but I guess this could be solved through changing the device tree compiler and telling it to ignore this class of error. So this is basically doing enabling certain components within the kernel, and that might not be as tasteful to some people. They might want to have like nothing in the kernel. So in another way, you could have per variant overlays if your bootloader supports applying overlays, and you have some way to specify like which device should have which overlays applied. So for Chrome OS hardware, we normally have one or more reference designs for a given platform, say for like MT8195 or Intel Raptor Lake or something. And then there could be one or more design deviations by the ODMs. And then we'll kick off one or more projects based on that design. And each project will have one or more SKUs tied to it. So the SKUs could be, different RAM chips, different storage options, different Wi-Fi chip, different display panel, different camera sensor, different trackpads, touch screens, whatever. The SKU variants go on and on. So for instance, the MT8186 SOC platform has 2 reference designs, and one wasn't actually chosen for anything, which is called, and the other is called Krabby, and we have like a DTSI file for it. And that got selected for the Tentacruel project, which has a number of SKUs, so that's a number of device tree files. And then there's a deviation, a derivation design called Steelix that was done by the ODM. And that produced 2 or more projects called Steelix and Magneton, and those also have a number of SKUs. So currently in tree we have like 1 device tree for every SKU. So the 8183 Kukui family has 10 device trees. The 8183 Jacuzzi family has 17. 8186 Corsola family has 10 and more to come. And basically because they are all derived or including the same DTSI files, you basically are duplicating most of the design into each device tree blob. And that adds up to kind of a lot. Now say we could take all the design aspects that are common to a given device and put them in a device tree blob and move all the SKU variations, such as a different trackpad or a different touch panel, into an overlay. So we convert basically the device DTSI file into a DTS file and all the SKU DTS files into DTSO files or device tree source overlay files. And in the bootloader, we ask the bootloader to basically take the base device tree blob and apply the overlay on top of it. And this basically allows you to deduplicate all the changes within a certain family, or for a certain device. So when you enable overlays, you basically increase the file size of the individual blobs because of symbols and fix-up tables, and omit if not ref ignored, and also extra vandals for every device node that has a label. However, if you have bootloader support for overlays and you package just the base device tree and the overlays, you can save a lot of space for your overall image. So in our case, in this case, there's like a 6.6% savings, or 6.7% savings if you just merge one device into the scheme I just mentioned. Of course, that number is minuscule compared to the actual kernel image size. Now, we could also expand this to have one device tree blob for the whole family of devices, and then we would have overlays for per device changes and per SKU changes, and that would be like 2 layers of overlays, and you would basically cut down all the duplicate device trees into just one base. Now the issues with this is this basically changes how the device tree files are managed. You used to have a bunch of include files, and then you'd have your final device tree source for your device. Now you would have one base either for the family of devices or for the device. Then you'd have a bunch of overlays that need to be stacked on top. And for for the maintainer has to basically know that these get stacked together, and also when viewing, it's kind of different, and also it increases the device tree blob size, and the delete property and delete node commands used in the device tree source no longer work. You can only use these two commands within the same device tree source file. Once they get compiled, the commands no longer exist in the blob. And also, device tree validation might not work as intended. Device tree validation happens with each invocation of the device tree compiler. So the base gets validated once, and then the overlays get validated separately. And however, the composite DTB, the base with the overlay, does not get validated. And also, you need bootloader support for overlays to actually use the overlays. So we could also use, like, instead of per SKU or per device overlays, we could change it up and use per component overlays, and you would specify one overlay for each component that you have, and you basically, in your fit image or whatever packing method you use, you basically specify how you want to stack your overlays. It's still a lot of files if you have a lot of component sources, but it does kind of reduce the number of combinations, because instead of combination, one device tree overlay for each combination, now you only have one device tree overlay for each component. I'm going to speed through this, sorry. So basically, the kernel would produce the base device tree blob and all the feature overlays, and the bootloader would still use the compatible strings that we had before, and basically pick out which configuration to use. But for the configuration, each compatible string would map to one base and then all the components it has. But then you'd have to either store this mapping somewhere out of tree or try to embed it into your overlays, which is either way is going to be messy. And some people might say it's hard to maintain. And the other possible way to do it is with fit image extensions. This was proposed by Simon Glass on the U-Boot mailing list. It basically describes a scheme for fit images to have extensions for certain configurations, and those extensions point to certain overlays that can be applied, and the extensions also have dependencies that you can specify. However, it's only a proposal for the fit image format, and it doesn't cover things such as how you store or manage the mapping and the dependencies. And also, it doesn't cover the case where you have multiple overlays when applied don't override the base, the root compatible string, and you have multiple configurations with the same compatible string. So for the non-conflicting I2C component change case, we can do coordinated probing for that case, and it works better than just having the kernel randomly probe each driver. Design and component changes will cause changes in the device tree files, and you'll have many more device tree files you have to maintain. And there's various options that you can do to reduce the duplication, but all come with trade-offs. And I don't think there's like one-size-fits-all solution to this. So the main purpose of this talk is to like show you what solutions I've come up with, and maybe you could discuss like what works for which case. And that's about it. So any questions? Yep.
Yeah, in Linux, device driver is all loadable, right? So do they have independent code that you develop?
I'm sorry, I don't quite get the
So how do you build a tree? Are they relocatable object? No.
A tree?
No, the device driver itself.
So I guess the device driver is within the kernel tree, and it's either built in or as a module separately loaded. And yeah.
That when you create a device driver module, do you have to create a position independent code? Or you don't know? That's okay.
So the scheme I use now is just basically when there's each module would have an init code, and in the init code it would create a platform device that matches the device driver, and the device driver or the manager device driver gets probed, and that will do all the probing.
Yeah, no, actually the word probe, I don't know, you use it probably different than how I understand it, but that's okay then.
Okay.
I think kbuild takes care of all the position independent code. Kbuild will take care of, and like when you load the module, your driver module, that'll take care of any.
You create the object itself, you have to make sure that it's independent, so that way you can load any way you want.
Yeah, kernel takes care of that.
You have a static address space, then the bootloader or whoever download the device driver has to know where to put it at.
Yeah, the build system.
You go to different device driver and see.
Oh no, this isn't like deciding which drivers to load. This is deciding which devices to probe.
This isn't deciding which driver to load. It's probing or accessing the I2C bus and checking which device actually is there, and then enabling that device node in the device tree. So you have devices listed in the device tree that are currently disabled, and you tell the kernel to enable this one.
Yeah, actually, for me, I2C is so simple, and you create it as a device driver, pretty costly.
Yeah, so you can't really do, like you can't do direct hooks in the kernel. You have to have something that starts it. Yeah.
I was just going to comment. I was surprised to see that your device tree, like when you do an overlay, your savings are not that high. At least from what I can see, in Qualcomm.
Yeah, so
I haven't taken measurements in a while, but in my mind, it's all those symbols and fix-ups. I can't imagine. I mean, I hope they're not taking, even if they take the exact same size, doubles the size of the DTB, you only need to have 2 overlays before it starts giving you savings.
Yeah, so the numbers are for the whole family that's bundled, but only one of them is converted. So it's like, I guess out of 30 DTBs, only 4 are converted. So it's not the whole thing.
Oh, okay.
I forgot to put the actual,
Okay,
one device numbers into here.
Okay, so this is only like a few have been converted.
Yeah.
And so, okay, got it. Yeah.
So,
but overall, I think one thing to look at is, as Chenyu said, is that even the device trees, all of them together are still not a giant chunk of the kernel.
yeah, so
right?
the whole bunch of device tree blobs is like, I don't know, hundreds of kilobytes, and the kernel image compressed is something like 12, 13 megabytes. Right. Yeah.
Yeah. No, I just was thinking you'd see higher savings. It's still a decrease, so I'm just surprised it's not more. I think doing just put all your nodes in the device tree, like you were talking about for I2C, and just see if it probes is actually really interesting, especially since I think hopefully we're going to start to see more devices trying to be supported upstream.
Yeah, so we have this, and also the ThinkPad 13S has this, and basically you have to do a dance with all the device drivers to make it not fall over.
Yeah.
And that's really ugly. So I talked to Wolfram last year about this, and I basically explained the whole scheme to him, and he's like, "Oh God, this is so."
Maybe we should talk to like Servana from Device Link and see if maybe he has thoughts on it. I don't know.
I don't think Device Links has any way to say these things are mutually exclusive. So the mutually exclusive group thing was proposed by Doug and then shot down by Rob. So.
I mean, he did give other alternatives. I think we could have made it work if we keep working at it. I think we can make that work. I think it doesn't solve every problem, but I think
Yeah, it only solves the non-conflicting one.
It solves the non-conflicting ones really, really well. Because it just totally gets rid of the whole explosion thing, right? Like you just see all the possibilities in the same device tree, and not having the overlays to conceptually worry about and all that, it's just really nice. And so it solves that problem well for a lot of simple cases, and it may be worth doing. And I think we could get it solved and we could get it landed with enough spinning and coordination. I think there's enough agreement that it's useful.
Yeah.
But I think also it's a little bit discouraging to work on because it doesn't solve every case, right? Like it doesn't solve the dual MIPI panels, and it doesn't solve, you know, some of the more complicated cases where you have all these graphs and things that don't live in the same device tree very well. So,
I mean, I just am thinking from the perspective of we're going to see more devices coming upstream, and so just it'd be nice if we had an easier solution for some cases. That
Yeah.
it feels like we want both.
Yeah. Yes. Yeah. Both. Yeah. Yeah. The only reason I was bringing up Servana was because you were talking about asynchronously probing, and that just in my mind brought up Servana. So, yeah.
Any other questions, or are we all headed to the closing game? Okay. I guess that's it then. Thank you, everyone.